All right. Hey, everybody. How are you guys? Good to see you. Welcome back. So it's Thursday, April the 16th. We're about to get underway for our Thursday class meeting. And this is for Intro to Philosophy at Orange Coast College, 6 p.m. to 9 p.m. Thursday night crew. Welcome one and all as you guys arrive to the meeting. I'm just starting the live stream a couple minutes early as we did before and as is now usual for us, to give people a little bit of time to arrive to the class and to get set up with their devices and everything else. So hopefully you guys are comfortable, doing well, staying safe, healthy, everything else. Tonight we're going to continue through these notes and we're going to talk a little bit about the metaphysics of time. So we have an interesting lecture on tap for tonight. And just a couple of general announcements that I'll make once we get a little bit closer to the 6 o'clock hour, just to make sure that there's as many students in attendance as possible when I tell you guys a little bit of information about what to expect over the next couple of weeks. Basically, nothing really is different, just I'm going to modify the due date of the second essay since we had 1 week of canceled classes. Basically, I'm going to move that due date out by 1 week. So that's something I'll go over with you guys. All right, cool. I'm just hanging in there, and we got about 5 minutes until class time, so I'll be right with all of you guys. Hey, Kitty. Come on, Kitty. Okay, here we go. Just trying to find our last lecture on my phone really quick. I'm going to go back into it and see what the last few things we spoke about were at the tail end there. All right. Let's just try and put this out there. What do you think? Good evening, guys. But he says, I'm not going to just assume that and take it for granted. I want to be able to prove it to myself. So he has a very slow and steady way of trying to make a case for that. But he starts from totally ground zero from scratch. So yeah, you know you exist because you're thinking. Me talking to you, you don't experience my experience. Nonetheless, every time I teach this, I think it's kind of funny. It's definitely had an experience my thoughts. So I've always said it's true that there's only one mind. Okay, seems like we kind of finished with some notes on Descartes, and we got all the way pretty much through the main points in meditation 2 that that you know that you exist as a thinking mind, even if nothing else is known for sure. So we're going to continue the same way. We'll be back in a week, and I'll have your guys. All right, cool. Good. All right. So yeah, anybody, if you want to chime in, chat a little bit, say hi. I'm right here, so I'll see all your guys' messages. It's always encouraged, to get the most interaction that we can get, and to have a little bit of feedback. It's good for all of us. So feel free to jump in and say hello anytime. I don't know if it's necessary to do this, but just in case, maybe I'll send a quick Canvas message to the class. Okay. Good afternoon. Hey, Shauna. Well, afternoon/evening. Yeah, nice to see you there for sure. Just sending this off to everybody. All right. So just as a little backup measure, I put a message out to the class. I hope you guys know that there's no need for such messages because, like you're expected to just always attend all the class lectures and stuff. It's Thursday at 6 p.m. That's what we all should know. But you're here if you're watching me and hearing me, and so you're in the right place. But I don't want people to start slacking off or whatever because we have a pandemic. You're still in school. You still got to attend your classes online. In fact, it should be easier for you to do that because you're just at home. Now I know everyone's dealing with their own issues and struggles, but at least in this institutional setting, we still have our standards. So you got to try and make these meetings, or if you don't, it's going to be worse for you. So just make sure you do your best to attend. Now, welcome back, everybody. Anybody watching, just again, like I said, say hello. I want to see you guys. I want to see your usernames and make sure that I'm, interacting with a couple of people at least. So, hey, Sherry, hey, Shauna, and others, if you're watching, don't be shy. Why would you be? After all, I mean, you're in the privacy of your own home. I don't even know what you're doing. So just feel free to comment and chime in at any point. So the midterms that you guys took a few weeks ago, those are all graded and done. So, you can inquire for your score anytime. Hey, Maria. Hey, everybody. I'm going to send the announcement to the class. I was just working on the grading kind of this afternoon a little bit more, so I didn't have my time yet to send the announcement, but I will maybe later this evening or tomorrow when I get up. And basically, anybody can send me a quick email and ask for their score, and then I'll be happy to send back your score with the written comments as an attached file so you can get the feedback on your individual responses. Hey there, Gilberto. Good to see you. So anyway, yeah, we're now into the second half of the semester, obviously. We've returned from spring break. Last week, we had one lecture on epistemology. That's a subject I'm, quite a fan of. Hey, Natalie. And epistemology is all about the theory of knowledge and the theoretical study of knowledge. So I just want to start today's meeting by kind of going over some recap and summary of those major topics last week. Let's see. Did I get a chance to send you guys this Gettier problem video? I'm not sure. Let me double check on this. I intended to do that. If I didn't, I'm going to send it to you now while we're here on, in our meeting. So give me 1 second. Oh, I did? That's the case? Gilberto, you guys saw the little Gettier Intro to Epistemology? Okay, good. Sorry, I kind of forget. I'm dealing with so many different classes that I sometimes forget where I sent the post out to. But that would have been a little helpful also for you guys reviewing the lecture from last week. Also, per the syllabus and the calendar, and I wanted to wait until 6 o'clock to talk about this. The next thing that's coming up is the second essay. Hey, Michael. Good to see you there, too, and everybody else. The next essay would have been due in 2 weeks on April the 30th. But I'm actually going to want to make a change to that, obviously, because we had to cancel 1 week of class for the sake of the COVID thing. So I'm just going to move the due date out to the 14th week. So it's going to be due May 7th, Thursday, May 7th, instead of Thursday, April 30th. So you're going to get one more week to work on it, and part of the reason for that is I want to give us more time so that we can develop a little more of this material and give you an additional essay prompt. So I'm going to send off the prompt for you between now and next Thursday, and then you're going to have more than 2 weeks to work on it. Oh, hey, Abraham, nice to see you there, another of my students. It says here, Maria, let's say we use the library for the book. What should we do? So your only access to this textbook was through the class, through the school library. I'll look into what's available. Some materials have been made digitally available for students that are not any longer able to get to the library. I'm not sure if this book is going to be one of those, but look, if anybody really needed any copies of any articles that we're reading, you can let me know, and I'd be happy to send you scanned images and pictures of the relevant pages so that you could view them digitally on your device, whatever it is. So let me know, Maria, if that's your situation, and I'd be happy to send off the files. Many of these articles are pretty short in terms of just page numbers, number of pages. So so it wouldn't be a big deal for me to send that to you if I'm not able to secure the copy of the book digitally in some other way. So I'll look into it, and then I'll give you an email tomorrow. Well, maybe you send me an email, initiate the exchange, and then tomorrow I'll be in touch with you about that exact topic. Okay, so yeah, anyway, next essay, I'm going to be giving it to you, the prompt, in between now and next Thursday, and then you will have over 2 weeks until the 7th of May to write it. And then again, like I said, your midterms are just now graded, so any students curious to know about their grade, be happy to tell you and share your grade, but I want to do that on a case-by-case basis. So just anyone that emails me, your grade is with me and I'll give it to you. Okay, so let's go back over at least some of the basic information that we learned last week. Last week we were studying epistemology. That was epistemology week. That's all about the theory of knowledge. So that's an important key area within the study of philosophy. So in epistemology, we ask questions about knowledge, like what is it? How do we attain it? What are the conditions required in order to have it? And what are the meaning behind certain important epistemic concepts like truth, belief, justification, and all of those matters. We started by reading the work of the ancient Greek philosopher Plato, and in his text called the Meno, he uses his teacher Socrates as the vehicle of expressing the theory of knowledge these ancient Greeks had. So in this Greek dialogue of Meno, Socrates, the great teacher who I told you about his life and death, he's discussing the topic of knowledge with the Greek general whose name is Meno. He starts by saying, suppose someone knows how to get to a place called Larissa, couldn't they lead other people there because they've been there many times and they know how to get there? And Meno says, yes, certainly. And then he says, okay, well, what if somebody didn't know how to get there, but they had a correct opinion? Couldn't they also lead people there? And Meno says, yes. And so that's like thinking about a person that knows how to get somewhere by heart versus somebody who's just using a map and they've never gone on their own. But the map is, in fact, correct. So why is it better to know as opposed to just having a correct opinion? The correct opinion is kind of shorthand for a true belief that lacks justification. In this case, lacking experience and previous experience. There's no reason to trust the correct directions, even though they are correct. Why is it better to know? Maybe because you will always get there, and the one that's just relying on correct opinion might get lost. The way Socrates puts it, it's like this. It's better to have knowledge because it's more secure than just a correct opinion. It stays with you and it stays in place. He gives this metaphor of statues made by a famous Greek sculptor named Daedalus. Those statues were so realistic in appearance that a myth emerged that if you ever had one, it'd be better for you to tie it to the ground with ropes. Why? Because these ropes would prevent the same beautiful statue from leaving as they were, as the myth indicated they would do if you turned around and stopped looking at them. So put them in the ground with ropes, then they'll stay put. Is it good to have a statue with or without the ropes? Sure, it's a beautiful thing, but it's better to have it with the ropes because then it doesn't go away. Now, what he's saying by analogy is that if you have a correct opinion, that's great, but it's better to have evidence and justification to back it up because when your true opinion is backed by reasons, it's something that you retain and that you don't forget about and that you don't change your mind about. So correct opinions that are grounded by knowledge, grounded by justification, are more secure and likely to be more stable and last longer. So why is knowledge better than just lucky guesses or correct opinions? Because it stays with you. So justification then serves the proper role of the ropes in the case of these statues. It's that factor which, when it's added to the statue, it keeps it there. And justification is that element that when you put it with a correct belief, it actually keeps you from changing your mind about it, and it allows you to retain it. So that was, Socrates / Plato's account. It's justified true belief that's knowledge, and justification is big because it upgrades a true belief from just being a correct opinion to being something that you do know, and it enhances it in the sense that it keeps it there and keeps it in your mind. By the way, these words that I'm using, like, for example, proposition. Proposition is the content, the meaning of a sentence. Like, for example, there could be two sentences that just have the same meaning, like, I don't know, I'm in the kitchen, or the kitchen is where I am. And those two sentences just express the same information, so they're the same proposition. When a proposition is true, it means that it matches the facts of reality, that what the proposition says corresponds to the actual facts. Like if I tell you I'm wearing glasses, this is a true proposition because it's something I am saying, but it's not just me saying it, it's actually really happening. So when the facts line up with the statement, it's a true statement. Otherwise, it's false. And then a belief is when you think that a proposition matches reality. In other words, when you think that it's true. So in case you have a justified true belief, Greek thought was that you had knowledge. But then comes Mr. Edmund Gettier, okay? Edmund Gettier said that that's not actually the proper analysis of knowledge, because you can give examples where a person has a justified true belief, but they still lack knowledge in that situation. So he gave two cases. In the first case, there's Smith and Jones hunting for a job. And they're the finalists for the job. Smith believes that Jones will get it. And he believes that because the boss had a free moment where he sort of whispered in his ear and said, yo, I'm going to give this job to the other guy, Jones, not you, Smith. So Smith now believes Jones will get the job. Also, just totally randomly, he counted the coins that are in Jones' pocket, and he saw that there was 10. So now he believes that the man that gets the job will have 10 coins in their pocket. And he's deducing that from the earlier belief, which is justified for the reasons I gave, that Jones will get the job and Jones has 10 coins in his pocket. Now, in the end of the scenario, there's always a little twist. The way this twist plays out is that the boss comes back in and he walks straight over to Smith and he says, hey, Smith, surprise, I'm giving you the job. I know I was saying Jones would get it, but I was just playing. Anyway, congrats. And so Smith gets it. He's the man that gets the job. And now it's just a random coincidence that he was not really aware of, but he happens to also have 10 coins in his pocket. So what that means is that at the end of our situation here, Smith believed that the man that has the job has 10 coins in their pocket. And that turned out to be true because it mirrors facts. But even though that's true and he believed it and he had his good justification for believing it, we would not say it's knowledge because the justification was formed on the basis of thinking that it would be Jones who gets it and counting his coins. So it's a mere coincidence, isn't it, that the belief turned out to be true if it was based on an entirely separate set of facts. So when you get some justified true belief, it's supposed to be true because of skill rather than luck, basically. If it turns out to be true just on the basis of dumb luck, then that doesn't seem intuitively to be a case of knowledge. Now, that's the first Gettier case. Remind me, did we talk about the other one, the one with Brown in Barcelona? Did we? I wonder. I forget if we did, but you could just quickly tell me. There's a second Gettier case. Does it ring a bell? That either Jones owns a Ford or Brown is in these different locations. Did we talk about case 2 or did I skip that one? Let me know. No, nothing on case 2. Okay, well, did you see information about it in the video maybe? If you watched the video, I don't know. That's something that you might have taken the time to do on your own outside of class. Okay, well, I mean, let me try and quickly give you a rundown about this second Gettier case, okay? Because there are 2 of them, and I don't want to leave behind the other one. So the first one that I just mentioned, the Smith and Jones job hunt scenario, that's probably the most well-known and widely discussed of his 2 examples. But there is, in fact, a second one. So let me just go over it really quick. In the second example, you've got, again, these two characters named Smith and Jones. Here's Smith. Here's Jones, other guy. Now, in this case, they're both co-workers. They both work at the same, office, same company. So they're co-workers, they know each other, they're employees of the same business. Now, here's something that Smith believes about Jones. He thinks Smith thinks that Jones owns a Ford. He believes that Jones owns a Ford, and let me tell you why. So just his thought bubble up here, where I put his belief in mind. Jones owns a Ford. Okay, so Smith believes that his coworker Jones owns a Ford car, like a Ford automaker make and model of car. Why does Smith believe that? Well, he has excellent reasons, so he's justified, just so that we're all clear. He's very justified in believing Jones owns a Ford. Why? Because Jones comes to work in a Ford, and he pulls up in the Ford. And when you talk to Jones, it's practically the only thing he ever wants to talk about. Like, yo, have you seen my Ford? I love Ford cars. I'm a Ford man. That's all I would ever drive. Do you want to ride home? I can give you a ride home in my Ford that I own. Check out some photos of me posing with my Ford. Everyone sees him in the Ford. He constantly is talking about it. So look, I mean, if you work with a guy and you see him in the Ford and he tells you it's his, and that's all you ever talk about with him, then you would believe he owned a Ford too. And you'd probably think I have good reasons for that because of my encounters with him and etc. So Smith believes Jones owns a Ford. Now, from here, the next little step in this Gettier case involves the concept of disjunction, which is an idea that is used in logic and in grammar. So in logic and grammar, we classify different types of sentences. Some sentences are called conjunctions. Those are and sentences. Like if I tell you that I'm wearing glasses and there's a cell phone on this table, that's a conjunction. It's a and statement. There's many of them. There's infinitely many of them. The moon orbits the Earth, and the Eiffel Tower is in Paris. So any random collection of two facts that you want to put on one table, that's like a conjunction. Another type of sentence, though, is what's called a disjunction. Now, what's a disjunction? That is an or sentence. Okay. What is it? It is an either or sentence or statement. Okay, so that's the concept of a disjunction. It's an either or statement. So if I tell you that I will either watch Tiger King or play the Nintendo Switch, that's a disjunction, and it disjoins these two possible actions, either the Netflix binge watch or the video game session, right? If I tell you, tonight I'm either going to have pizza or tacos for dinner, that's a disjunction as well. And it states a disjunction of two cases, either the one case, having the pizza, or the other, having those tacos. Now, with a disjunction, the terminology is used of individual disjuncts. In every disjunction, there are two disjuncts. You could call it the left or the first disjunct versus the right or the second disjunct. And it's just determined by the order that they appear in the speaking or writing of the sentence. So if I tell you that, the person will either vote for Trump or Biden, what's the first disjunct of that disjunction? Just to make sure you're tracking what I'm saying. Give me that feedback. Person says, I'll either vote for Trump or Biden. I think that's probably true of most people anyway, because there's pretty much only two nominees at this stage. But anyway, in that disjunction sentence or statement, what is the first disjunct? You heard me say it, right? The person says, I either vote Trump or Biden. What is the first disjunct? To vote for Trump, and the second disjunct would be to vote for Biden. All right. Now, new question, everybody. According to your common sense and just understanding of this meaning of this word, how many of the two disjuncts do you think have to be true for the whole statement to be true? There's two disjuncts, so how many of them do you think have to actually be true for that to be a true statement? When a person says either A or B, for some A or B sentence, for some A or B disjuncts. What do you think? It's not both. Sorry, Sherry, that's wrong. So let me give you a reason why. Well, but before I do that, give me a different answer. How many of those disjuncts have to be true? It's not both. No, Shauna. It's an or statement, okay? So how many do you think have to be true? Give me a different answer, please. Excuse me, what? How many? Yes, one. Okay, and think about it, right? If I told you I'm going to eat either pizza or tacos for dinner, how many of those different things would I have to have eaten to have spoken the truth? If I said I'll either have pizza or tacos for dinner, and then you come over and you see that I'm eating pizza, did I make a true statement? Did I? Yes. Because what did I say? I didn't say I'm going to have pizza and tacos. That would be a conjunction. I said I'll have either one or the other. Okay, so if I did just one but not the other, it's still true. If you see me with the pizza, I spoke the truth. If you see me not with pizza but just with tacos, it's still that I spoke the truth, because what I claimed in the beginning was that I would do one or the other. Talk about the voting, right? Say someone says, I'll either vote for Trump or Biden. If they voted for Trump, they spoke the truth because they said they would vote for one or the other. If they voted for Biden, they also spoke the truth because they claimed that they would vote for one or the other. Now tell me this, what would it have to be for my statement to be false if I told you that I would either eat pizza or tacos for dinner? How would that turn out to be a false claim or statement? What would have to be the conditions for that to be false? What do you think? The person says, I'm going to either order pizza or tacos off this menu. What makes their statement false? If what? Yes, if both are false. So if you come over and you see that I'm eating sushi, you could be like, wow, you really didn't say the truth. You said you'd either get pizza or tacos, but you're having something that is neither one, okay? Or like a burger or whatever, exactly. So with a disjunction, with an or statement, just one of them has to be true for the whole thing to be true. And the only way it will be false is if both of those disjuncts are false. Can we understand how conjunctions are different and sentences? If I told you that I would get pizza and tacos, now that's a different type of sentence, isn't it? In a conjunction, therefore, how many of the conjuncts have to be true for the whole thing to be true? What do you think? When one says they're going to vote, no, forget voting because you can't vote twice. When they say they're going to eat both pizza and tacos, I'm going to eat pizza and tacos for dinner. It's a weird dinner, okay, but maybe I would do that, I don't know. What would make that false? Well, first of all, you're answering the good question, Natalie. What would make it true is that I did both, right? So if you come over and you see me with a platter and there's like some pizza and tacos on it, then it was true that I ate both pizza and tacos, or that I ordered them both. But it would be false if you just saw me with one or the other, in case I claimed both. So either or is not the same as and. And is a conjunction and it requires both, or is a disjunction and it only requires at least one. Now, okay, that's just a little backstory so that you guys understand the next element of this discussion. Let me ask you a new question. Is this statement true? Professor Vulich is either Professor Vulich is wearing glasses or the moon is made of cheese. Currently, is this a true statement? Either Vulich is wearing glasses or the moon is made of cheese. Is that true? What do you think? Is that true? It is true, yes. Good, you got the right answer. And why is it true? Because of the first disjunct alone. Yes, I'm wearing glasses and we can see this. So it's true that either I'm wearing glasses or anything else. The second disjunct kind of stops being relevant, because as long as the first member of the disjunction is true, I can disjoin it to whatever else that I would like, and I would still have a statement which is just as true as the first one, because no claim is made of both. The claim is instead made that one, at least. And so given that I'm wearing glasses, it's true that either I'm wearing glasses or you own a dog. Either I'm wearing glasses or, I don't know, we've hit the coronavirus peak today or something like that, you know? So now with regards to Smith. Smith already, I told you, believes that his coworker Jones owns a Ford. And he has his justification and good reasons for believing that. Now, let me erase a little here so I got some more room. Let's imagine next that Smith, he's a huge fan of logic, and he knows all about this disjunction concept. And he also knows about the closure principle that I mentioned last week, which says that if you have justification for believing one proposition, and then you notice that it entails a second one, then when you deduce that second one from the first, the justification carries over to the second one. So you're also likewise justified in believing the second. So like, since you're justified in believing that I'm born in the 80s, you're also justified in believing that I'm older than you, because that is entailed by the proposition that I'm born in the 80s. Forgive me for any student that maybe is also born in the 80s, but speaking of the general case, that would be one entailment. Okay, so now Smith believes that Jones owns a Ford, and because he loves logic and he's really weird, he just decides to form three beliefs which use that statement as the first disjunct in an overall disjunction. So he forms these three beliefs, Mr. Smith. Okay, the first one is that either Jones owns a Ford, or, now let me introduce one other character. Okay, I'm about to tell you about this guy whose name is Brown. Now, who's Brown? Brown is somebody that Smith used to know. They were good friends, but they've kind of lost touch. And it's been a long time since they ever talked. And right now, Smith does not know where in the whole world Brown is at, or even if he's still alive, but he could be anywhere. So because Smith already is justified in believing that Jones owns a Ford, he next decides to believe that either Jones owns a Ford or, and then the right-hand disjunct is going to say a place name of where Mr. Brown could possibly be. Okay, and he gives three different locations. So either Jones owns a Ford or Brown is in Boston, Massachusetts. Second one, either Jones owns a Ford or Brown is in Barcelona, Spain. The third one says either Jones owns a Ford or Brown is in, now this is a little not as well-known city, but it's Brest-Litovsk. It's like an Eastern European capital. But anyway, that's the third one. Either Jones owns a Ford or Brown, long-lost Brown, is in Brest-Litovsk. Okay, so what you're seeing here are the three beliefs that Smith forms just based on his evidence that Jones owns a Ford. He has no knowledge at all of the whereabouts of Brown, and he's randomly selecting these three cities. Okay, so now here's our little Gettier twisty plot twist ending. Ready for this? So here's how it turns out. Jones, the co-worker of Smith, that everybody thinks he owns a Ford, it turned out to be an elaborate hoax. He's a fake. That's not his Ford. He's renting that car, and he's just showing it off to people, claiming it that he owns it, but he's really just trying to, flex with this rental car, and it's not actually his. So he does not own a Ford. False. Does not own a Ford. But, and this is just a total coincidence, something that, 1 in a million, but it just happens as a total random thing that Mr. Brown is in Barcelona. He's over in Barcelona, Spain, doing whatever. And Smith does not know that. So here, which of these three propositions written on the board then ended up being true in the end of our situation here? You got three. Which one actually turned out to be true? Just the number of which one. Which one is the one that actually became true in the end, according to the features of our scenario here? Which one? What do you think? Well, I think you'll know. It's not a guess. It's 2. Correct, 2. Why though? Well, 2 is true because one of its disjuncts is true. But it's not the one that Smith had evidence for. It's the other one that he just randomly put on the table for no reason. So look at number 2. Did Smith believe number 2? Yes, we went over that. He believed it because he thought he knew for sure that Jones owns a Ford, and he just disjoined some other random bit of information to that belief. So he believes this disjunction number 2. And he actually was justified in believing it because he was already justified in believing the first half of it. And since the full disjunction is a logical consequence of that, he's also justified in believing the whole disjunction based on the evidence he has pertaining to Jones. But even though he's justified in believing it, and it turned out to be true, the reason that it became true had to do with the part of the disjunction that he had no information about, and the part of the disjunction that he did possess justification for is not the part that made it true. So his evidence is out of order with the facts that make the proposition true. So this is supposed to yet again strike the intuition of the reader as a case where a person has got a justified true belief, but it's not really knowledge, because yet again, it's just randomly coincidental that it turned out being true given the manner in which he collected his evidence, because his evidence had no bearing on the whereabouts of Brown. So since that's the factor that made this disjunction true, we would say that it's kind of a random fluke that this was a justified belief that was true. In the ordinary circumstances, if Brown had been anywhere else in the world, then the belief that he had formed based on this evidence would have been false. So 2 cases by Gettier. In each of them, as weird as they are, what we're supposed to take away is that someone had a justified true belief, but they did not really know that thing because of the random luck that intervened to make the proposition which they believed with justification turn out to be true. Sherry, here you have a question. But if there's a false element, then it's not true in the knowledge JTB statement, right? Well, the proposition of interest is not false. The proposition of interest here is number 2, which is true. It is true, given our description of the situation, that either Jones owns a Ford or Brown is in Barcelona, because Brown is in Barcelona. In the first Gettier case, the statement that the man who gets the job has 10 coins in his pocket is also true. It's just because it's Smith himself instead of Jones who he thought would get it. What you're talking about is not something being false. What you're talking about is the justification being formed in the beginning for a proposition that ended up being false, right? Because Smith had evidence that that Jones would get the job, and that turned out not to be the case. But the thing that he deduced from that justified false belief did turn out to be true. Same here. Smith has a justified but false belief that Jones owns a Ford. But what he deduces from that, proposition 2, is not false, but rather it is true due to the second disjunct. So let's not confuse ourselves into thinking that because the justification was based on a false proposition, that doesn't mean any proposition which is entailed by it cannot also be a justified and true proposition. Okay, so that's just a little recap for us of the Gettier material. Then we talked about Descartes, and I kind of wanted to also do a little bit of review on him. When it comes to René Descartes, we looked at meditation 1 and 2. And so Descartes' whole goal was to try and discover what we could find out as totally certain, because he thought that if we knew what was certain, we could use that as the foundations of this really growing, rapidly advancing enterprise of scientific knowledge. He thought that had to be based on something rock solid, and that means it's got to be based on something that we never have doubts about, that we'll never have to change our minds about. So what's this certainty? He tells us we'll find it if we use what's called the method of doubt. The method of doubt, well, we talked a little bit about meditation too, Sherry, because we talked about the I think, therefore I am concept. But there's a little more in there that I'm going to add. So is this what you're referring to by your comment? We talked as much as the concept that I think, therefore I am, and the fact that you exist is known by the very existence of your consciousness. So we got that far into meditation too. But let me digress, okay? Descartes is trying to find out what is certain. He says, use the method of doubt to determine what is certain. The method of doubt says, assume to be false anything which can even possibly be doubted, okay? And by using that method, he thinks we will find out what is not capable of doubt. So once the method is applied, he says everything from your 5 senses could all be doubted. Everything that you think you are seeing, tasting, touching, hearing, and smelling, perceiving, basically, in whatever way, all of that could be false because maybe what you're experiencing is not even reality, but just a dream. So if you've been dreaming, maybe the things that you think you're seeing are not even real. Maybe it's all just an illusion, and it's just found and seen within the dream state. Maybe your life is some type of, I don't know, matrix-like existence, or that you live within a computer simulation, or whatever the case is. But he goes with dreaming as the possibility that leads to skepticism. So because you cannot discount the possibility that you're dreaming, you cannot say your senses are working. So therefore, he says, let's assume that that's completely false. After that, he said, maybe there's a little more certainty when it comes to math and stuff like that. 3 plus 2 is 5. How could anybody doubt that? That doesn't even seem to depend on the existence of the environment around you, just the formal definition of these numbers and the mathematical operation of addition. But he says even there's room for doubt. Okay, why did he say there's room for doubt about math and all those concepts? Well, he started by saying maybe God could mess with you on that because he's all powerful. But he quickly withdraws the thought, because he says even if God could do this, he never would do it, because it would be contrary to his perfect benevolence. So let it be not said that God would do so, even though he could, but maybe an evil demon that is not God, therefore not omnibenevolent, but still capable of manipulating your perception of the world. Maybe an evil demon could be the one responsible for making even your beliefs about math and stuff like that turn out false. So that's where the first meditation ends, and he says everything is subject to doubt. But with the second meditation, where it begins, is that he says there's actually this one thing that is not touched by the method of doubt. One thing remains totally certain, and now we get to the point that I was mentioning there, Sherry. What is this one certain thing that nobody can doubt according to Descartes? Or at least you can't doubt. I don't know if I should say everybody, because that's part of other minds. But what's the one and only thing that an individual cannot have doubt about, according to Descartes? And what's the reason? You cannot doubt that what? Let me see what you can say. Nobody could doubt this. The whole point of his method of doubt was to find out what this thing was. So what is it? This thing that's not subject to doubt. It's not the 5 senses. It's not math. It's that you exist, right? It's that you yourself exist. And how is this something you cannot doubt? Well, just think about it. The very fact that you're considering any questions, the fact that you're contemplating or thinking about anything at all, definitely establishes that you're some thinking thing with a mind. So maybe the world's a dream, maybe none of it's real, but even if that was so, the fact that you're having that dream and thinking about it means that you, the thinker, at a minimum, must be real. Now, what is it that you know yourself to be? He says, you do not know that you are a body. You do not know that you have the same physical appearance that you think you're seeing when you look in the mirror. Maybe in reality, you have no physical frame whatsoever, and you're just a disembodied soul. And you're not privy to that because you're now in this current dream state. So if nothing else, you're a thinking mind, but whether or not you have a physical extension or body, that's something that he says could still be doubted. Okay, now the last little part of meditation 2, since we're talking about that and going over it in review, was this bit about how we perceive physical objects in the deepest sense. According to Descartes, even when we look at objects with our 5 senses, like this table or chair that I'm sitting on or whatever, or imagine, your immediate surroundings, wherever you're watching this at, the knowledge that we have of those physical objects and bodies, he says even that is more deeply rooted in the power of the mind and its intellect, rather than the physical sense organs like your eyes, ears, nose, and tongue and all that. So why does he think that the more deep and abiding source of knowledge about objects comes from the mind? Okay, well, he gives us this example of a piece of wax. So let me talk to you quickly about this wax example. So this is Descartes' example from Meditation 2, all about the wax. So I'm going to try to draw a cube of wax using whatever artistic skill I may or may not have, okay? There you go. Perfect 3-dimensional cube of wax. Now, here's what he says about it. Imagine that it has certain qualities that you can perceive with your 5 senses. And we're going to give one quality for each of the 5 senses. So first of all, vision, your sight. When you look at this wax, let's say that it's blue in color, so it looks blue. That's the color. So blue is the visual aspect. Now, suppose this wax is a scented piece of wax, like a scented candle. So it's got a floral scent, meaning it smells like flowers. Okay, next up, he talks about, so back in his day when he wrote this, 1641, and still to this day, sometimes wax is made out of beeswax, okay? And that means that it actually does have the ability to be edible, and it retains a faint trace of like honey flavor. So if you ate a small piece of this wax, it tastes like honey. So we got sight, taste, smell. Now, when it comes to touch, it's a solid cube of wax, so it's hard to the touch. It's in a solid state. Plus, it's cold. So that's the tactile sensation, the feeling of the five senses, the touch sensation. So it feels hard and cold. And then to get in the auditory aspect, he refers to how it would sound if you struck it like with your knuckle. So if you hit this piece of wax with, let's say, a knuckle or whatever, it's going to make a rapping, knocking sound when you hit it. So it makes a sound when struck. Okay, so now I want you to look at this, description of our piece of wax here. And what I'm going to draw is just a little time indicator. This is lowercase letter t, subscript 1. What that just stands for right now is time 1. So at one initial time, this is how the wax is at that time. It's looking blue, it's smelling like flowers, it's tasting like honey, feeling hard and cold to the touch, and making that sound if you strike it. That's at time 1, though. But I want to tell you a little story about what happens to it over some time and what it looks like later. So suppose that after time 1, we expose this wax to like a high flame, So here's, for example, the flame. Okay, it's giving off heat, And this wax was exposed to that flame. Then at some later time here, T2, subsequent after 1. Okay, so this is later on after exposure to the flame. Let me tell you what's going on with the wax now. It's been melted down. So instead of being in that cube shape, it's just this kind of goopy puddle of wax, right? Now, due to the exposure to the flames, it's lost all of these qualities that were seen within the wax at one initial time. So because it's been heated up so hot, it's not got that blue appearance anymore. It's been charred to like a brownish, blackish color. The smell. It used to have this floral smell, but because it's been incinerated so, at such high temperatures that it now just smells like charred, like burnt wood or whatever, The third, tasting like honey. Well, it's been heated up to such an extent that now it's lost that gustatory aspect, and instead it's just got a bitter, charred type of flavor to the tongue. It used to feel hard and cold to the touch when it was in this state, but now it's no longer hard, it's liquefied, and it's in a state of being a little warm because it's been heated. And then finally, it used to make a knocking sound when you struck on it. But now, given the fact that it's in a puddle, it would either make a splashing sound or no sound at all, and you're actually just hitting the surface on which the thing is laying. So here's something that he wanted to point out. All the qualities of the wax that were perceived by the five senses have changed across this time period. But does the wax still exist at time 2? Despite these changes that it's gone through, does the wax still exist? And the answer there is yes, it does still exist. Now, what Descartes says here is that when you want to think about something and you think about it in its deepest essence, you have to think about what its essential properties are, what its necessary attributes are. And essential or necessary attributes of something are the kind of attributes that are not optional, that it has to have to even be the thing that it is. Okay? Non-essential attributes are qualities that something might have, but they're not mandatory. It's like if they have them, it's just optional. But they don't need to have these qualities in order to just be that thing that they are or to exist. So let me give a quick question to you, and then we'll come back to our wax example in a minute. So think back to geometry, okay, guys? What would you say is having four sides a necessary attribute of being a square? So I'm asking you about one element of the definition of squares, the geometric form of a square. Is having four sides necessary to being square? Is that an essential attribute, or is that a non-essential attribute concerning squares? The four-sided element. Do they have to have those? Yes, they do. Okay, good. Clearly, yes. That's the right answer. In order for something to be a square, by definition, it must have four sides. It's not as though that's just something that some squares have four sides and others don't. It's by definition of square that they must have four. Here's another question. Is being, let's say, the color red one of the essential attributes of squares? Is being red an essential quality of squares? Let me know. What do you think? Four sides is essential for squares. Is red essential for squares? What do you think? I bet you know. No, it's not. Good. So a square could be red, but it doesn't have to be. It could be blue, green, or any other color under the rainbow. That's not something that's needed in order for a square to be a square. So now, take view of the wax. This wax had these attributes that you could perceive with your five senses at one initial time. But were these attributes of the wax essential attributes or not? Was it essential that this wax looks blue, smells like flowers, tastes like honey, feels hard and cold, and makes a sound when you strike on it? Are these essential elements or attributes of the wax? Or are they non-essential? Hopefully we're tracking this discussion and see what you give me. The qualities that are written under that block or cube, they're non-essential to the wax, exactly. Because they're attributes that have been eliminated across time due to the change that it undergone through the exposure to heat, but the wax still does exist. So when you think about essential attributes of this piece of wax, we have to think about the qualities that have not changed in the interval between time 1 and 2. So what are essential qualities that this wax does still have? Things about it that it had at time 1 and it still is the same at time 2. When we think about those attributes, we're going to really get deep into the inner essence of what objects are. So what are those essential attributes? He thinks there's 3 essential qualities of the wax. Okay, so the first one is that it's something that is extended. And the term extended in the usage of philosophers and physicists just refers to anything that occupies some region of space. Okay, so occupies space. Okay, so every physical object is extended necessarily. If a thing was not extended, that would mean that it literally is just nothing. It has no parts, it takes up no space, it's got no mass, no volume. But like me and you, of course, our bodies, that is, they are extended in space. If your body's placed in water, it will displace the water. The seat or whatever that you're sitting on right now, your body occupies that physical position and it occludes other objects from being in the same exact position as it. So take view of the wax. Was it extended at time 1? Yes, it was extended in this cube form. Is it still extended at time 2? Yes. I mean, has it changed its outer contours? It has. It's become a little liquefied and it's become misshapen, but it's still extended in space. So despite the fact that it's lost some of those non-essential perceptual attributes, it remains extended across all possible changes. Even if we took this wax and we, split it into a whole bunch of different parts and, disassembled it and distributed them far away from each other, all those little bits would still, each piece, be extended in space. So that seems to be something that objects never lose, no matter what happens to them, even if they get rearranged or cut up into bits. A second attribute of the wax that is essential is that he just uses the word flexible. Flexible. And the third is changeable. Flexible just means here that it's able to be reconfigured into different surface forms. So like it can occupy and take on different shapes and different outward forms. At this point, it was shaped in the position or shape of a cube. Now it's like a goopy puddle. If we really wanted to, though, we could collect this molten wax, put it back into a mold, and flex it back into a different configuration or the same one again. We could turn it back into a sphere, a little pyramid, or whatever other thing we would like. So it was flexible at this point in time, and it still is flexible at this later point in time, even though the shape, precise nature of the shape has changed. Changeable just means capable of undergoing alteration of its attributes. So at this time, it was capable of being melted down and losing its flavor and taste and smell. And at this point, it's also capable of undergoing future changes as well. So what Descartes is saying here at the conclusion of this wax example is that this wax could just be thought of as a stand-in for any object that exists in physical space, whether it's your body or whether it's the table and chair that this board is sitting upon. All physical objects, when you think about them at the root essence of what they are things which are extended in space, that are flexible, meaning can be reshapen, and that are changeable, that can undergo alteration of their attributes or properties. And he says that when you think about these essential attributes, you will realize something important, that these are not apprehended through the five senses. The five senses only ever see the non-essential, temporary, perceptual qualities of a physical object. The deeper lying essential attributes of it can only be understood by the mind, which has to contemplate how it would survive all possible changes and still retain certain core features. That's something that is not perceived at a moment of time. It's a judgment that the intellect makes when it considers the comparison between the thing at one time and another time. And even if you think about yourself as a physical object, right? Looking at yourself in the mirror, you look a certain way, but you didn't look exactly the same way when you were, like, let's say, a baby. Now, I know that the genetic features were there and they would be developed in a way that would lead to your mature appearance, but it's a different looking being. And when you're much older, maybe your hair will be gray, or, maybe you will have lost or gained a certain amount of weight, I don't know. But even if you undergo all those changes, the object that your body is still endures in a way that represents the manifestation of those deeper traits. So a person's hair color, height, mass, volume, number of fingers or toes at one moment in time is perhaps not the most essential way to think about the physical object that they are. And so much is true of all other objects too. So in closing, as I'm recapping and adding a little bit to our discussion of Descartes, he says, with the method of doubt, at least initially, all that you can really know about yourself is that you are a mind which thinks. The existence of your body and all of its physical features is subject to doubt, but even when you contemplate the nature of objects that exist in space, it is your mind which gives you a more true understanding of them than your physical five senses do. So he really prioritizes the insight that we have using our intellect rather than our five senses. And this kind of just, again, reinforces his claim that what you most essentially are is a thinking mind instead of an embodied animal. And so, Sherry, you say this, you know how in class you would write the key points on the board? Can we do that with the live casting too? Yeah, well, I mean, that is what I'm doing. These are the key points. I wouldn't have written anything different in the class meeting. This is supposed to be a minor point, this exploration of wax. You're supposed to take away these points, that the essential attributes of the wax are that it's extended, flexible, and changeable. You're supposed to be able to see that by means of the illustration that the perceptual qualities which it did have been eliminated across the passage of time. Now, I wrote all attending to the notes in the exact same way. So I'm not going to do something different than what I would have done in class, and I haven't been. Maybe it's harder for some people to keep track of all the notes at once because I have to constantly erase them since this is a very small board. If it was in class, maybe you would have the illusion as though I'm writing more notes because there's a full board with like notes everywhere and I never have to erase it as much. But no, my method's not changing. I appreciate your comment, but I'm teaching in a very detail-oriented way. And if there's any point you want me to go over again, then ask a question about the specific point and we can go over that. All right. So next up, we're going to go on. Okay, so to the next topic in this class. We are moving on from epistemology for the moment, and we have a few more subjects in the docket to go over. So what's next is time and the metaphysics of time. So I kind of want to talk to you guys a little bit about the general idea of metaphysics, and then we're going to study some important authors who discuss the application of metaphysics to the understanding of time. So I'm just getting my notes here. Okay. Okay, so in philosophy, there's a lot of big, important subjects of study. One of those is the philosophy of religion that we've all reviewed in good detail. There's also ethics, which studies morality and right and wrong and what the basis of moral claims is. Then there's epistemology, which we've just now kind of looked at. sorry, just modifying my brightness on the monitor. Okay, and so another major area of philosophy that we're going to now look at is metaphysics. So what metaphysics means or represents in philosophy is just kind of a very deep investigation into the nature of reality and what exists. Okay, so and the main general question that is found within this overall field is what exists and what is the nature of the things that exist? So that's metaphysics. The original use of the word goes back to the Greek philosopher Aristotle from antiquity. And in his usage, it just kind of meant to go beyond the physical. But in its everyday usage nowadays, it kind of just generically refers to, again, as you see here, a precise, focused investigation into aspects of reality, trying to find out what really exists in this reality, what goes beneath the and behind the appearances that we see, what's the real deep inner essence of reality, what things exist in this universe and world, and what's the nature of them, what's their description or explanation. There's all kinds of questions that metaphysicians can ask. So there's a wide range of possible topics. One of them could be, do we have free will, or are we just determined to act as we do? What is the nature of the self, and how does it persist across time? For example, you exist right now, but when you were a little baby, you were much smaller. And in fact, you don't even have any of the same cells in your body anymore. They've all been replaced over that span of time. So how is it that you still are the same person if you have no physical continuity to earlier stages of yourself? What's the criteria for personal identity over time? Well, there's all kinds of interesting questions like that in metaphysics. But the one that I chose for us to focus on here in this class is time. So we're going to look at the metaphysics of time and try to get a very clear understanding, if we can, of what the most current theories of time are and how they shape our understanding of the universe and our position within it. So on the metaphysics of time, we're going to start by reading the writings of Albert Einstein. Okay, so yeah, just get my book here. Einstein, Albert Einstein, the great scientist, physicist, and philosopher, great public intellectual, well known by all, I'm sure. Such an iconic household name. He was born in 1879, and he lived until 1955. He had a very important life. He is responsible for revolutionizing the understanding that we have of time and space with his Nobel Prize-winning papers in physics published in 1906. So he was very young at that age. He just graduated college. I mean, a couple years back, and he'd been working as a patent clerk in a patent office in Germany. And on his free time, he would just read papers in physics and try to write his mathematical theories out and his physical theories out that try to explain the nature of space and time. When he's only about 26 years old, in the year 1905, 1906, he published on the electrodynamics of moving bodies, which is known as the general theory of relativity, and followed by the special theory of relativity. That was a revolutionary piece of work. It changed our entire understanding of time and space. It basically took us away from the older Newtonian conception, which said that no matter what is happening in time and space, the two realms are separate. According to Newton, time and space didn't have any influence on each other. So basically, no matter how fast or how slow an object is moving through space, that could not possibly affect the rate of time's passage, that they were independent of each other. But what Einstein was able to show is that that's not true, that time and space are actually integrated into one unified structure called space-time, and the rate at which an object passes through space in terms of its velocity does affect the passage of time relative to other observers in space. So he really did have these radical results that showed us that time and space are integrated and that the way time passes can vary and in fact shift from observer to observer depending on their state of relative motion compared to other observers. So we're going to try and get very clear on that. Now in 1906 he wrote his groundbreaking work that he won the Nobel Prize for, and he's like 25, 26 years old at that point. 10 years later in 1916, he wanted to make these ideas a little bit easier for more of the public to digest. So he wrote a book called Relativity, which popularized some of these ideas. This is just a way of trying to bring down to earth a little bit some of the very heady concepts that average people might not have been capable of understanding because of the math and the technical logic and physics that was involved. So in Relativity, he tries to present these ideas to a wider audience in ways that are a little bit easier to digest or comprehend for lay people. So from this book, our text has taken a snippet away, and they've retitled it, and I'm going to talk to you guys about that piece of this book. Okay, so erasing this, so I have a little additional room. This is called in our text, Time and the Relativity of Simultaneity. Time and the Relativity of Simultaneity, 1916, from Einstein. Okay, so when it comes to Einstein, I mean, he's a name that I'm sure everybody's heard, and even just the appearance that he has is kind of like the iconic stereotype of like the genius, scientist or intellectual with the crazy big hair and everything else and the kind of rumpled overcoat. But not everybody who's heard his name or recognizes his appearance knows much about the ideas that he had and why he's so widely appreciated in physics and in philosophy for those ideas. So I'm going to try and serve to you guys the very basic crash course elements on Einstein's theory of relativity. So here's how we begin. Opening my book to the page. So he asks this question to start us off. He says, I want you to consider a hypothetical situation really fast. Suppose that there is a railway embankment, okay? And so basically a railroad track. And lightning strikes the rails at 2 points, A and B. So let's designate the 2 points. Here's A, here's B. And lightning bolts strike at those 2 points on the railway. Now, let us assume that these two lightning bolts strike simultaneously. That sounds like it's a very simple statement to comprehend. But Einstein says, not so fast. Think about it. Tell me, what does this mean, the statement that the two lightning strikes happen simultaneously? What would you say if somebody asked you, what does that actually mean, though, that they happened simultaneously? Now, it's not so easy to give an answer to this question as it seems at first. Even Einstein points that out. He says, you might recognize after thinking about it for a moment that answering this question is not so easy as it seems, because any attempt that you may have to answer the question, what does simultaneity mean? Or what are two simultaneous events mean? Any attempt to answer what simultaneous means is going to probably lead you to say something like this. They happened at the same time. But happening at the same time is just elliptical for simultaneous. So can anybody give an attempt to say what simultaneous means without just saying something that is equivalent to, they happened at the same time? What do you think? I'll give you a second if you want to try it, but it's not so easy. And therefore, it's actually, totally fine and makes perfect sense if you have difficulty supplying an answer. But the question is this: what does it mean to say the events happen simultaneously? Definition, explanation, what does it mean? Anybody? What do you think? The lightning bolts strike the railroad simultaneously. What does this mean? But try not to just say they hit it at the same time or they occurred at the same time. Nobody? Nothing? Just take a second. You have anything? No guess? Well, I guess not. If you don't have a guess, that makes some sense, I suppose, because what Einstein says is that it's going to run around in a circle. If you just try to say simultaneous means simultaneous, then you haven't provided a informative answer to the question. And he actually says that unless we have a definition of simultaneity that is so precise that we could actually conduct an experiment to determine whether the two events were simultaneous or not, we may be using a word that doesn't actually have any well-defined meaning. So we have to have an understanding of this concept that is so clear that by means of it, we could perform an experiment and actually determine using that experiment whether those were two simultaneous lightning strikes or not. Let me read then to you what he says, and he puts it in his words here. He says, lightning has struck the rails on a railway embankment at two places, A and B, distant from each other. I make the additional assertion that these two lightning flashes occur simultaneously. If I ask you whether there is meaning to the statement, you will answer my question with a decided yes. But if I now approach you with a request to explain to me the meaning of the statement more precisely, you find after some consideration that the answer to this question is not so easy as it appears at first sight. Now, he says this in the next paragraph. He says somebody might reply by saying this: who cares? I can't define it, but do I really need to? It seems like it's something that we just understand intuitively. And when I say simultaneous events to anybody, they understand what I mean. So who really cares if I'm able to give you a precise definition? Can't we just sort of use the word and sort of shrug our shoulders when people ask us what it means? Einstein says, no, you can't do that. As a scientist anyway, you can't operate with a concept where you just sort of wave your hands and say, it means something. I don't really have a clear understanding. You have to have a detailed understanding of it in order for it to function in the realm of physics and science. There has to be the means by which you could test whether or not the events were simultaneous. And he says, until you give me the mechanism to conduct a test of simultaneity, we may be using a word with no meaning at all. And that's what he says. After some time, perhaps the following answer would occur to you. The meaning of the statement is clear by itself. It needs no further explanation. It would require some consideration if I were to be commissioned to determine by observation whether in the actual case the two events took place simultaneously or not. Einstein replies, I cannot be satisfied with this answer for the following reason. Suppose that as a result of ingenious considerations, an able meteorologist were to discover that the lightning must always strike the places A and B simultaneously. Then we would be faced with the task of testing whether or not this theoretical result is in accordance with reality. We encounter the same difficulty with all physical statements in which the conception simultaneous plays a part. The concept does not exist for the physicist until he has the possibility of discovering whether or not it is fulfilled in an actual case. We thus require a definition of simultaneity such that this definition supplies us with the method by means of which we can decide by experiment whether or not both the lightning strikes occur simultaneously. So he says, until you can give me an experiment to conduct to determine whether the events are simultaneous or not, then you don't really have any kind of clear understanding or definition of this concept. And he says, as long as this requirement is not satisfied, I allow myself to be deceived as a physicist, and of course the same applies if I'm not a physicist, when I imagine that I'm able to attach a meaning to a statement of simultaneity. And I would ask the reader, do not proceed farther until you're fully convinced on this point. So he's basically just saying, we have this task set before us now. Let's try and understand what it means for those two events to be simultaneous. And let's try and understand it in a way that would allow us to conduct a physical experiment to test whether they're simultaneous. So what is the test for simultaneity? Okay, here's what he suggests that we do. So take the interval between A and B. Think of A to B as a line segment. Question, is there a midpoint in between A and B? Is there one midpoint that lies in between A and B? What do you think? Geometry, everybody? What do you think? You see A and B on the line, on the railway. Is there a midpoint? What do you say? Yes, of course there is. What's the midpoint? Let's call it M. Every line segment, everybody, has a midpoint that lies in between. So it's the point that perfectly bisects the line. Michael, I don't know why you're saying no. A to M is equidistant from B to M. Every line you can cut in half. Okay, so let's place an observer at this midpoint M. There's an observer. This observer being at midpoint M is exactly halfway between A and B. So he's the same distance from A as he is from B. Okay, now let's make sure that this guy here at the midpoint M is positioned far back enough from the two lightning bolts and the two regions where they're going to strike. Make sure that he's far back enough away from it so that he can see both of those points in one field of vision. Why do you think that's necessary? If he was too close, let's say, to see them both at once, then could he verify simultaneity by looking at one and then quickly switching his gaze to the other? No. If, let's say, he was so close to A that he sees the lightning strike there, but then he has to quickly avert his gaze towards the other direction, then even if he saw A lightning bolt, quickly shifts his face towards B and then sees B, he would not have been able to prove or determine whether they were simultaneous because he couldn't see them both in one field of vision. So he has to be placed far back enough at a midpoint such that he can actually see A and B in one common perceptual field. If he's not able to do that by means of his distance, then let's place some type of mirrors inclined at 90-degree angles so that it will refract the light. Therefore, he's able to observe the 2 points in space in his one field of vision. Okay, now, here's the suggestion. If this observer who's standing still at midpoint M observes the two events and sees them in one visual field happening at once, then given his condition of observation, we would say they're simultaneous relative to him. But we have to make one more stipulation for this to all check out. So let me ask you guys a quick question about vision and how it works. Say you're looking at your computer monitor or whatever device that you're seeing this live stream on right now. So you can see the live stream just with your eyes open. Question, how is it that you're able to view images? How does vision even work? What is the procedure or process that's leading you to see my face right now? How are you able to see it? Because I'm nowhere near you physically. So just how are you able to see this image? What's the way that that actually works? How is your brain seeing a professor talking? How does the image get received by your brain and by your eyes? Tell me how. Is it magic? How does it work? Give me a little scientific description of how vision basically works. Just don't have to be detailed, obviously, but you know, in the big picture, how do you see things? How do you see the things in your environment? Rods, cones, optic nerve to the occipital lobe. This is a little more detailed than I was actually looking for. I'm thinking more about the physics of it instead of the biology. So what is the physical process that allows you to see the thing that you're looking at right in front of you? How does it get to your eye? What do you say? There's like 10 of you guys in there. So what do you think? Okay, let me ask you another question. Well, there you go, light. That's kind of what I was going for. If you close your eyes, can you see things? Like when your eyes are closed, can you see this lecture? And then you open them back up, you see it again. But when the eyes are closed, do you see anything? Of course not. Why is it that when your eyes are closed, you don't see anything in your environment? Let's talk about that. Why is it that if you close your eyes right now, you'll not be able to see this? It's a fundamental reason, and it has to do with exactly what you just said, Sherry. The reason that when eyes are closed, you don't see things is because with the eyes closed, you're blocking what? You're blocking light from reaching the lens of your eye. Exactly. The flesh of the eyelid is like a shade that's pulled down over the eyes, blocking any incoming light from being received, and therefore you can't perceive the images. So when you look at something, the way you're able to see it is that light reflected off the surface of that object travels to your eye, and then it is collected by your retina and processed by your brain as visual information. But there's a little bit of a time lag between the emission of the light source from the object till the time it gets to your eye. Okay, so some of you guys may have studied a little bit of basic astronomy, and you might have learned that, like, for example, when you look at stars, what you're seeing is this object as it was a long time ago, because it takes, in some cases, many, many years for the light to travel from whatever distant part of the universe the star is at to reach your eye here on the surface of planet Earth. In fact, even the sun, which is 93 million miles away, light rays directed at the Earth from the sun take about, I think, 8 minutes or something to reach the Earth, because going at the speed of light, which is 186,000 miles per second, a 93 million mile away distant object takes that amount of time to reach you. So when you're looking at this computer monitor that you're looking at right now, you're actually seeing it as it was a split second ago, given the fact that there's a little interval of time, minute and infinitesimal, but a small interval of time between where the light bounces off the surface of the computer screen and then makes its journey towards your eyes as it propagates through a vacuum of space. So next up, let's make sure that we understand one thing about our little situation here. This guy is only going to be able to verify that the two events here are simultaneous if we assume that the speed of light is fixed and that it never changes. So basically, we have to assume that the speed from A to M is the same velocity as the light which is traveling from B to M. Okay, but if the speed of light is constant and it remains equivalent from the direction of travel A to M as it is from B to M, then the fact that they arrive at the midpoint at the same moment and he sees them at the same moment, given the fact that they arrive to M at the same time and that they're traveling the same distance, if they've gone the same velocity, we could thus deduce that they emitted from the two origin points A and B at the same moment. In other words, were simultaneous. But if we did not hold this assumption that the speed of light was always fixed, then this would not actually be able to verify simultaneity. So let me give you a second example modifying this slightly. Imagine that A and B are two runners, and what they're going to do is run a race, and M is the finish line of the race. Now, since it's a race, they both have the same distance that they have to travel to finish it. Say that this is like, whatever, a mile, and this is a mile, equivalent distance from A to M and B to M, the two runners running towards that finish line. But suppose that A is twice as fast a runner as B, okay? He's twice as fast, he's half as slow as A. If that's true, and they reach the finish line at the same point in time, question, did they leave at the same point in time or did they leave at different times? So if A is twice as fast at running as B, and they arrive at the finish line at the same moment, photo finish, knowing that A is twice as fast as B, question, did those two individuals depart from the start line at the same moment or not? A is twice as fast, B is twice as slow, they meet at the finish line. Question, did they leave at the same time or did they leave at two separate times? It's not a probably, this is deductive logic, so it's a necessary answer. They did not leave at the same time. Why? Who left first if they meet at the finish line when one of them is twice as fast? Was it B that left first and got a head start, or was it A that left first? Who left first if the faster runner by a factor of 2 gets to the finish line at the same time as the slower runner? Who left first in that case? The slower one left first, exactly. If this person is twice as fast and he barely catches up at the same point in time to the other half as slow runner, then that means that the slower one was given a head start of half the distance. And since he's half as slow, that was all the time he needed, like the tortoise and the hare, to catch up to him at the very end, except this is a different tortoise and the hare, where the hare actually, I guess, catches him at the end. Okay, so understand that. That is why we have to assume that the speed of light remains constant and it does not alter in speed like these two different speed runners. If light is not like the slow runner from this direction and the fast runner from this direction, but just a constant fixed velocity from all directions to all others, then we would be able to deduce from his observation point that the common receipt of the two light signals at M implies that they were emitted at the same time and not at two different times. So, since light is traveling at the same speed over the same distance and reaching the same destination at the same time, that means that they each left from their respective origins at the same time, okay? And that's what he says here as I read it on page 456. He says, after thinking the matter over for some time, you offer the following suggestion with which to test simultaneity. By measuring along the rails, the line AB should be measured up and an observer placed at the midpoint M of the distance AB. This observer should be supplied with an arrangement which allows him visually to observe both places A and B at once. If the observer perceives the two flashes of lightning at the same time from this position, then relative to him, they are simultaneous. Now he talks a little bit about how we have to stipulate and assume that the speed of light is fixed for this to actually work. He says, I am very pleased with this suggestion, but for all that, I cannot regard the matter as quite settled, because I feel constrained to raise the following objection. Your definition would certainly be right if only I knew that the light by means of which the observer at M perceives the lightning flashes travels along the length A to M with the same velocity as along the length B to M. And then going down a bit further, he says that light requires the same time to traverse the path A to M as for B to M is a stipulation which I can make of my own free will to arrive at the needed definition of simultaneity. So thus we've kind of defined simultaneity of these two lightning strikes. What does it mean then to say that the two events were simultaneous? It means exactly this, that an observer standing motionless at the midpoint between the two events would have seen the two events happening at once if we assume that the speed of light is constant. Using this definition of simultaneity, that when the light signals received by an observer from the two distant events come to the individual at the same time, we can thus assign simultaneity to any two events. And this is actually exactly the way that we organize our behavior according to the clock. Take, for example, the clock that we use to make sure that we're on time to all our different appointed tasks. Like, you know that this class starts at 6. And so you can imagine that the direction to attend this live stream at 6 can be interpreted in the following way. Using a measuring instrument with a reliable pointer, when that clock face has the pointer indicating 6 p.m., you should be able to visually observe that time indication on the device while you see this lecture beginning. So make those two events be simultaneous. The observation of the time indication on your watch or time measurement device, and the observation of the light signals coming from your computer monitor as the lecture starts. Now, the weird thing, though, is this, and this is where it's going to get a lot trippier and weirder now. Even though these two lightning strikes are simultaneous from this person's perspective, we're going to show now that the same two lightning strikes will not be perceived as simultaneous to a second observer who possesses a different state of motion than the first one here. Okay, so we're going to add a second observer to our scenario right now. So let's consider this addition to the example, and this will show that simultaneity is not absolute. So suppose we have a train now. Here's the train, and this train is traveling along the railway in the direction of travel towards B and away from A with this constant velocity V, okay? And we have an observer who is in the moving train traveling with that train's state of velocity. Now, because he's in the moving train and he's standing still over here, those two observers have two different frames of reference. The observer standing still off to the embankment side regards all events relative to his motionless observer position. The observer in the train possesses the velocity of the train, and he observes all events relative to that frame of reference, the moving train. And each one of us does possess our own frame of reference depending on the degree of velocity that we possess relative to other observers in the universe. So where he observes the two events from the position off to the side, he's going to observe the two lightning strikes from his perspective on the moving train with that constant velocity v. Now, suppose that this observer on the moving train, as he travels along the railway from left to right, passes through the midpoint that this person is aligned with at his other position. Let's call the midpoint, as seen from the moving train's vantage point, M prime. So it's the midpoint with prime added so that we just can distinguish his midpoint observation from his. Now, as he passes through this path of travel, imagine that he perfectly aligns with this observer along this plane of the midpoint. So he's at M prime and he is at M. Imagine that while he passes the midpoint here, M prime, this observer is passing that midpoint at the exact same time that he's conducting his observation from his stationary position. So he's at M, looking at the two lightning strikes, seeing them happening simultaneously. And at that very moment, this guy is traveling to the right and passing through M prime. Now I want you to imagine this in your mind as though it's like a video playing through. In the video version of this, you would see our train guy going, and then I'm going to hit pause for a minute. When am I hitting pause? I'm hitting pause at the exact split second when he lines up with M, okay? So question, at that split second of time, are both observers at the midpoint in between A and B? Hopefully we can just give a quick yes or no to that. As the observer is traveling with this velocity to the right, I just hit a freeze frame at the moment where he's on that plane. Would he be at the same midpoint? Wouldn't he be at the midpoint between A and B, the moving observer? Yes, okay? He's gonna be aligned with the midpoint at that point in time. I'm imagining this as a playthrough video, which I just hit pause at the split second that he's touching that midpoint. Now, if I unpause or hit play, what's gonna happen to this observer that was for just that half momentary second at M prime? What will happen to him after we release the pause button? The guy who's on the train traveling with velocity v. Where will he go? What will happen to him if we continue viewing our hypothetical recording of this? The guy on the train will go where? As we continue the playthrough of his, journey on this train track. He will no longer be at M prime. He will be carried toward the direction of B and away from A. So now think about this question. Will this observer see the two events A and B happening simultaneously if he conducts his observation while he traverses that midpoint at the exact moment that this person standing still conducted his observation at the midpoint? Will he see A and B happening simultaneously, the one who's in motion? We've already established that relative to him, they appear to be simultaneous. The second observer, though, you're correct, Sherry, and Gilberto, I see your comment too. He'll pass the midpoint exactly. So the secondary observer who's on the train traveling to the right, he's not going to see the two things happening simultaneously. Let's see if you can judge which of the two he would see happening first. Which lightning strike is going to be viewed as happening first from the perspective of our moving observer who's going in the direction of travel to the right? He surpasses the midpoint because he's constantly moving with velocity v. He passes this midpoint while he conducts an observation, seeing them simultaneous. You gave me the right answer, that he will not see them simultaneous. So that means he sees them happening out of order. And you're correct, Sherry, that the first one he would see would be B, and then afterward he would see A. But tell me now, since you gave the right answer, if this is not just guesswork, why is it that he sees B happening first instead of both at the same time? The other guy saw them happening at the same time. So why does the one who's now in motion see it being B first? That's correct, but why? I think you know. If you could just sort of try to put it on the table and say, why do you think that he will see B occur first? Because exactly, he's closer to it. And remember how we've talked about the transmission of light signals to your eye in order for you to perceive objects. The light signal coming from B has a shorter distance to travel to reach our moving observer than A does. Because since he does his observation while passing the midpoint, A has a longer distance to reach to get to his eye, and B has a shorter distance to reach. He's closing the gap between himself and B and expanding the gap beyond the midpoint of himself and A. So these light rays don't move instantaneously. They have a very high degree of velocity, but they still have to take time to get to the moving target of your visual system. So because this man is standing still, and because the two lightning rays arrive at his eye at the same time, he saw them as simultaneous. But a second observer who possesses this velocity and who intersects with the midpoint while he conducts an observation will be carried closer to the second lightning strike, further from the first one. And since they have got an asymmetrical distance to reach him, A and B in his case, traveling at the same speed, they cannot reach his eyes at the same time. One of them is going to be playing catch up while the other one gets to him first. because he's closer to that one than the other one, basically. Okay, so here, I'll read it to you from the book, and then you can see. So he says this, up to now, our considerations have been referred to a particular body of reference which we have called the railway embankment. We suppose a very long train traveling along the rails with constant velocity v, and then direction of travel indicated in figure 1, which is actually shown on page 456. People traveling in the train will use the train as a reference body. They regard all events in reference to the train. So every event which takes place along the rail line also takes place at a particular point of the train. Also, the definition of simultaneity can be given relative to the train in exactly the same way as with respect to the embankment. So the following question arises. Are two events, two strokes of lightning A and B, which are simultaneous with reference to the embankment observer, also simultaneous relative to the train? And we shall show directly that the answer must be no. When we say that the lightning strikes A and B are simultaneous with respect to the embankment, we mean this, that the rays of light emitted at the places A and B where the lightning occurs meet each other at the midpoint M of the length A to B of the embankment. But the events A and B also correspond to the positions A and B as seen on the moving train. Let M prime be the midpoint of the distance A to B on the traveling train. Just when the flashes of lightning occur, this point M prime naturally coincides with the point M, but it moves towards the right in the diagram with the velocity v of the train. So if this observer sitting in position M prime in the train did not possess any velocity, if he was just sitting there in a state of rest, then he would remain permanently at M, and the light rays emitted by the flashes of lightning A and B would reach him simultaneously. But in reality, he considered with reference to the railway embankment, he is rushing towards the beam of light coming from B, while he is riding on ahead of the beam of light that is coming from A. So therefore, the observer will see the beam of light emitted from B earlier than he will see that emitted from A. Observers who take the railway train as their reference body must therefore come to the conclusion that the lightning flash B took place earlier than the lightning flash A. And we thus arrive at an important result. Events which are simultaneous with reference to the embankment are not simultaneous with reference to the train, and vice versa. And this is the relativity of simultaneity. This means that every reference body has its own particular time. Unless we are told the reference body to which the statement of time refers, there is no meaning in the statement of the time of an event. Before the theory of relativity, it had always been assumed in physics that the statement of time had an absolute meaning, that it is independent of the state of motion of the body of reference. But we have now just seen that this assumption is not compatible with the definition of simultaneity. So we therefore have this really revolutionary and radical result. Now, it's being explained to you here in terms of these two lightning strikes in this hypothetical scenario. Let me ask you some follow-up questions, if we can, about the scenario given here. This is kind of a trick question, so I want you to ponder it for just a moment, but see if you can give me any type of answer. Sounds like a simple question, but hey, the two lightning strikes, A and B, at the end of this whole explanation of Einstein's work, what's the answer? Are they simultaneous or not? Are they simultaneous lightning strikes, or are they not simultaneous lightning strikes? What do you think? And I'm giving you a hint. It's kind of a trick question. So what do you think? Which one? Simultaneous, not simultaneous? What do you think? What do you say? We've got two lightning strikes. We've described the two observers. We've described the different outcomes of their two observations relative to these two events. So are they simultaneous events, or are they just not simultaneous events? Which one? Okay, Sherry, I thought maybe you might give that type of answer, and I have to unfortunately say no. So the answer is that it's relative. When you say in reality, yes, that's not correct. There is no objective reality according to which they're simultaneous. It's relative. It depends on the observer and their state of motion relative to the observed events. all we can say is this. The answer is also not no. The answer is not yes, and the answer is also not no. The answer is that it's relative. From this observer's vantage point, they are perceived as a simultaneous events. From the observer who's in motion, they're seen as not being simultaneous events. But you don't want to misunderstand this. It's not like one of them is correct, and then the other one is seeing some illusion that is generated because they're moving around. That's not the right way to think about this. Both have equal claim to have seen, yes, she's back. Both have equal claim to have seen the thing from the correct perspective, as it were. Because let me tell you, there is no privileged observer or condition of observation. You may think this guy's standing still, and so he's seeing like the real facts. But every object is in motion relative to other objects. You may think you're sitting still right now, but your position on the surface of the Earth, which is rotating around the sun at a very high degree of speed and also tilting on its axis constantly. So when we talk about something being at rest, we're only speaking about it as relative to other things which possess a different state of motion. Therefore, there's no objective fact about whether they were simultaneous events or not. And that is the sort of really deep and weird, trippy, mind-boggling thing, that two events can no longer be assigned any objective linear sequence or order. And it gets even weirder. If you want, I can expand on this just a bit. So suppose we have a third observer, okay, going in a different direction on a separate train. So this observer is going in the direction of A, away from B, with velocity v, constant speed, in the other direction. Now suppose that when they go in this direction, they pass by the midpoint. We call it m double prime. So suppose that for a split second in time, as all of these people are moving and he stands still, they're all momentarily aligned along the midpoint. Like you'd see, like, you know, a vertical line where all three of those little stick figures are all in alignment. But that would be like for a split second, because these two are in constant motion. So for the same reason, going in the opposite direction, which event would this third observer see happening first out of A and B? The observer going in the opposite direction of travel would see which of the two events as first. What do you think? It's easy enough to say. It's just, you know, it's like the opposite, but I want you to say it. So, you know, I want to be too didactic. I want to sort of get that feedback. So the third observer, you follow me? He's going from right to left. Which one does he see happening first out of two lightning strikes? Which one? And there's two letters. I mean, come on, it's a 50-50, whatever you say, but I don't think you have to guess. It's pretty simple. Which one is seen first by the third observer who's in the opposite direction of travel? Yes, it's A. Why is that the case? Because he's in the opposite direction of travel, so he's closing the gap between himself and A and expanding the interval of space between himself and B. So now we have like a third possible observer with yet another description of the order of events. To observer 3, A is first, B is next. To observer 2, B is first, and then A. And to the initial observer here standing still, it appears to him as though they're simultaneous. The difference in the three accounts simply has to do with the amount of time it takes the light signal to get to them, given where they're at and how fast they're moving, or whether they're moving at all. But it's so strange, because it really, when you start to understand the deeper implications of this, it actually implies that there's no objective order to any of the events in time at all. So think about moments that you would right now regard as being in your future. Like, you know, you, I don't know, finishing this class, taking the final, being able to get out of quarantine because they have a vaccine. You know, maybe if you're really young, you know, getting a little older, getting married, having kids, eventually getting retired. Those are all kinds of stuff that you think that has not happened yet. That's in the future. Objectively, there's no fact about those events yet because they have yet to happen. But what this implies is that it's not just the two randomly selected cases of these two hypothetical lightning strikes. Any two events whatsoever in space-time can be reordered according to a different possible observer's condition of viewing the events. So, you know, there are hypothetically possible observers that would see events that you regard as occurring in your future as already having happened, and vice versa. Because if we can simply reorder the events here according to the context of the observer, then that means there's no fact at all about what the order of them was. So like to this person, when he sees B, B is happening in the present and A lies in the future. To the other individual, A is seen happening in the present, whereas B lies out in the future. So which one happens before the other? There's no longer any objective fact about that. Remember when I just talked to you guys about how if you look out into the night sky, you're seeing these stars and you're seeing them through a time delay, as it were, because it takes quite a while for the light to reach your eyes. Okay, now imagine that we had super strong telescopes. We do, in fact, have those, but imagine even on orders of magnitude stronger, such that we could actually view life forms in distant planets doing whatever they're doing, right? Now, when you saw those things through the telescope, what you would be seeing are those life forms in what would you think, the past or the present or the future? So I have a question here from Sherry. The key takeaway is that simultaneity is subjective as it is relative to the observer. This is evidence that time is relative to the motion of observer. That's absolutely correct. Yes. And Sherry, I see you now commenting on my most recent question. If you were looking in my example at distant life forms through a telescope, and you could see them from your position on the surface of the Earth, you'd be seeing them as what you would regard in your past, right? Okay. Now, imagine yourself on the other end of that whole situation. Imagine the alien life forms over there in that distant part of the universe with telescopes pointed in our part of the cosmos. They're looking over in our direction. We're looking in their direction. You just said that we would look at them and say they're from the past, or the images we see of them come from the past. But if they were pointing their telescopes over at us, then they would see us and they would regard us as being things that existed in the past. So who's really in the past? It's relative yet again. So it's very mind-boggling and weird, but implications that arise from this are that all the events of space-time are equally real. All of the events that are contained within the whole past, present, and future are equally real right now, and then they're all as real as each other. So you as a little baby is a real moment of space-time which will permanently exist. This present moment is certainly real and you're experiencing it now, and all future moments, not just of your own existence, but the entire space-time existence of all objects are real and existent. This has to be conceded to make sense of the simultaneity results here. Because if, again, two events like randomly selected examples of lightning strikes can have different orderings depending on the context and position of the observer, that means that any two events that you like could similarly be perceived as happening in a different time sequence. And therefore, we can no longer say that there's only one past, present, and future, but it just depends on which observer in what part of space and their state of motion relative to the other observers and events. Very strange, because it starts to make you wonder, do we even have free will? If this theory is true, and it is the consensus view of modern physics, so this is not merely philosophical speculation, it's actually got considerable empirical backing by real tests that have been conducted using instruments that we can use to measure these things. So it starts to make you wonder, is there any such thing as free will? If all the events of space-time exist, and it's not only the present that exists, then what are we? We're just creatures that have consciousness, and we see the unfolding of our lives, but we're kind of, I guess, in that sense, helpless to do otherwise than what is predestined to happen, because all the events are fully laid out. Very strange idea. Now, there's a couple of more aspects of Einstein's work that are not necessarily talked about in the book, but I like to refer to them. In the full version of our class, I actually would have brought in some video to show you guys a little bit of like scientific documentaries that talk about his ideas in some more depth. But I want to help you out with like a couple of other fun and very weird aspects of Einstein's theory of relativity. So next, I want to talk to you guys about a phenomenon that is a consequence of this theory, which is called time dilation. Okay, so time dilation. Imagine that we have what's called a light clock. So what these two things are here are just planes of glass that are reflective, like a mirrored surface. So imagine that we take a photon of light and we excite this photon so that it strikes the top plane of this mirrored plate. Because it's reflective, it's going to reflect the photon back down. And because the bottom surface is a reflective surface, it's just going to perpetually go back and forth, up and down. So basically you have a bouncing photon that's going in between these two glass plates. And because the consistency of light speed is constant, we can convert this into a time measurement device. So this now becomes a time measurement device called a light clock. Imagine that for each cycle where the beam photon touches the top and bottom, 1 second of time passes. So you're just going to see this photon beam going up and down perpetually between the two planes, counting a second for each cycle. Now say that we have 2 such light clocks of identical construction. And imagine that they've both been issued from the factory that produces them at the same time. So they're like twin light clocks, identically constructed, the same age, and in perfect synchronization with each other. So like as one goes up and down, so does the other, and they're just keeping time in unison with one another. Okay, now let's say we have an observer here with this bottom light clock, person who's just watching the light clock do its thing. Now, let us say that this light clock that's with the observer is going to stay at rest. So it's not going to take any acceleration. It's going to remain at rest, just cycling up and down. But the one above, its twin, we're going to accelerate this one very quick to the right with a high degree of velocity, maybe even approaching the speed of light, right? So this one now is accelerating off like a race car to the right. And this one is just standing still. Okay, couple questions. What is going to be the arc that is caused by the photon of the motionless light clock going up and down? I'm just going to tell you that it's going to be a simple vertical line, straight up and down, like this. Well, my finger's a little bent, but it's a straight up and down because it's not moving at all. So if you're looking at it and you're standing still and it's standing still, you just see this, up and down. But this one has now been accelerated very fast. From the standpoint and perspective of this motionless observer, what do you think will happen to the angle of approach of this top photon moving between the two plates in the accelerated light clock? What do you think about that? Like, what would be the angle that it's going to take as it completes those cycles from top to bottom? The one that's in motion while you stand still. Just imagine the visual. You're standing still. It's going to be accelerated to the right very fast, and you're looking at it. What do you think is going to be the visual experience of this observer who stands still and sees this light clock that goes very fast to the right? How will the angle of approach of the photon that's bouncing look from his perspective? What do you think? What kind of shape will that wave, if you like, take? That one photon in the light clock that's been accelerated, unlike its counterpart that stays at rest. Well, okay, Maria, you said that it would look like a horizontal line. Not quite horizontal, though, because that would mean that it possesses infinite speed, right? It eventually, of course, has to still bounce, right? So it's not exactly a horizontal, but you're on the right track. What's another possibility, if you follow my description here? It's in motion, so you're right, it's no longer going to look vertical. But straight horizontal is too much, because that means it never even touches the top and bottom. So what would it look like as it makes its journey along each cycle to the motionless observer who watches it as it takes off? What would that look like, the angle? Horizontal wasn't quite it, but let's see who can give me another one, another look. You say like the Nike logo? The Nike logo is a swoosh. So, it just goes up. But, the thing's going to come down too, right? So we're getting a little closer, I guess. But there's a certain word for this type of direction of travel. Somebody said horizontal, that's not it. Like the Nike logo is a little bit too informal. Let's go with geometry, everybody. Like, what's the type of angle that it's going to form? What do you think? What do you think? I need the feedback. I need you to tell me. So just tell me, what's that angle going to look like? Seen by the motionless observer, observing the fastly accelerating light clock, which goes to the right. The photon beam bounces between the top and bottom, but now it's being accelerated. So what do you think the person's going to see in the way it travels from top to bottom? It's not vertical, okay? I said that. This one's vertical because it's staying put, straight up and down. The other one's racing to the right, so you don't see a vertical path, obviously, because it's moving. So what do you think will be the trajectory that it appears to take? Well, it's not a right angle. A right angle is a 90-degree angle. There's no gradualness. So you're saying like a sine or cosine wave? Yeah, it's sort of like a diagonal. I was just hoping anybody would say the word diagonal, okay? So like diagonal. Look at that. Hopefully, I don't know if your mind was thinking of such a thought, but this is what you should be thinking of, right? Because as it's being accelerated, it takes a longer angle of arc for it to complete one cycle, given the fact that it's now being stretched to the right with the acceleration of velocity v. This is an effect that can be seen in other wave-like structures. Let's go with the example of the Doppler effect. That has to do with sound. So here's the Doppler effect. And you guys, I know, have experienced this yourself. So if you're standing still, and let's say a car rushes past you, right, going pretty fast. Say they're honking their horn, like, you know, I don't know why, but they're just honking and they pass you in their car. Now let's describe the difference between the, yes, pretty funny. Let's imagine the difference between the sound of that horn to the person in the car that's honking it versus to the person standing still outside the car as it passes them by. Because it's a different qualitative auditory experience for the two observers. And there's specific physical reasons for that. So imagine yourself, put yourself in this position. You're standing there on the street, car comes by honking and then drives past. Now, here's a fact. The pitch and frequency of that horn sound, it modulates as it approaches and as it drives away. Now, as it's coming closer to you, what do you think is going on with the pitch of the horn? Is it becoming higher or lower in frequency? What do you think? Do you have a memory about that or just a judgment? The approaching motorist honking versus when they're driving off to the distance. What's the quality of the pitch of the approaching motorist horn? It's higher pitched, exactly. And there's a specific physical reason for that. So this sound works, again, by the propagation of sound waves that the ear collects and then the brain processes. So when a sound wave is coming from an object that possesses velocity and it's coming at you, that compresses and scrunches up the sound wave so that it has a higher amplitude and trough, and that produces the higher pitched frequency. As it drives away from you and the distance between the object emitting the sound wave increases from your ear, that stretches out the amplitude and trough of the same sound wave and produces a lower tone. That's why if you're standing still, this approaching car, which then drives off, sounds like this as it approaches. It gets higher and then lower. Now, and I'm not the best at impersonating the horn, but now if you're in the car, you don't hear that modulation because there's no degree of variability between the distance of the object that makes the sound and your body because you're traveling with its velocity. So when you're in the car, you just hear but people outside of the car will hear that frequency shift. The pitch shifting, which has to do with the velocity of the approaching car versus the one that's further in the distance, is somewhat parallel to the phenomenon spoken of here. So from the position of the person standing still with the stationary light clock, you just see the wave, if you want to call it that, as being perfectly vertical. But the one that's being pulled away from him with velocity, depending on the degree of velocity, it's going to be a more gradual slope. So now, suppose that we took this light clock and we accelerated it at that velocity for a while, maybe letting it orbit the Earth several times, going close to the speed of light. And this one, its twin, remains at rest, still ticking away, but at rest with the motionless observer. Imagine that after some degree of time, we allow this fast-moving light clock to return back to a resting position with its twin. So it's orbited Earth, Now we're putting it back and reuniting it with its twin. Okay, relative to this observer, which of the two light clocks has counted more seconds after they are reunited? One of the two has ticked away more seconds, and one of them has done fewer. Which of the two has gotten more counts, more clicks of the photon beam touching the top and bottom? Which one has counted more seconds after they're reunited, following a period of time where the top one was accelerated really fast and therefore stretching out the angle of approach of each cycle? Which of the two do you think then would have counted more cycles? The bottom one has more seconds, exactly, Maria. And the reason is very clear. It's because it only has the short distance of the top to the bottom of the plate to travel in order to elapse one cycle. But from the perspective of the observer who's sitting still, the one that has been accelerated takes this much longer journey to complete one cycle, and it becomes more gradual the faster it's going. So this one is going to have counted fewer seconds when it's been reunited with its twin. But that is just very, very strange, because these light clocks started off being the same age and being in perfect sync. Now they're different ages. The fast-moving one has aged slower than the one that has remained at rest. So now light clocks that were issued of identical construction and timing have got two different ages. And it's because the one that was accelerated is passing through time slower than the one that was at rest. And this is a true principle about the theory of relativity that holds across the board. Objects that are moving fast through space are passing slower through time than other objects or observers that possess less velocity relative to the initial one. How weird is that? It gives rise to another paradox and puzzle in physics that's called the twins paradox. Okay, so imagine that this observer has an identical twin. Okay, so identical twins, everybody, are basically people that are the same age. I have triplets that are my siblings that are all the same age, so it can happen, of course, that people, are born by the same parents, the same mom, right, roughly the same time. So identical twins, as you would know, go through life being basically the same age, having the same birthday. Well, suppose that we have this guy and an identical twin here, and we put this identical twin on the light clock while it's accelerating very fast. When this identical twin comes back and reunites with his twin, who's going to now be older? The one that stayed at rest. Just like this has counted more seconds, the observer who's at rest with it has experienced more time than the observer who was zooming around with the velocity of the fast-moving light clock. And, from the perspective of the guy who's moving fast, just like that driver who doesn't hear modulation in the frequency of the horn that they're honking, he just sees the photon beam bouncing straight up and down because relative to him, he possesses its velocity with that frame of reference. So the delay is seen by an observer who's in a different reference frame, who sees that longer angle of approach because relative to him, the light beam has to carry itself across that arc. So how strange is that? Identical twins, right? Identical twins, but now they're not the same age. One is older than the other because they didn't move at the same velocity as the other. And that's so strange. You would have thought that time cannot possibly pass at different rates for different people. This is the essential insight of Einstein's theory and how it radically transforms the Newtonian understanding that came before it. According to Newton, no matter how fast or slow two objects are moving or how fast or slow two observers are moving through space, time always passes at a constant fixed rate for everybody. It's neither faster nor slower for anyone else. It would have seemed bizarre under those understandings to think that two identical twins can achieve different ages just because one was moving faster and the other one was either at rest or moving relatively slower. But this is exactly what is the case according to the theory of relativity, and it's been very well established through physical experiments. Am I still holding office hours? Yes, Sherry, and we can do that anytime. Maria, so theoretically, if you move backwards around the sun at the speed of light, would you be younger? No, you would not. It's not that it makes you younger. Let's just understand what's being said here. You would go through time slower. Time does not go, backwards or anything like that. And you yourself don't experience yourself becoming younger. It's just in relation to other people that are aging, at the regular rate, you're going to see a dilation in time that you experienced. It's not going to be experienced as less or more time either. So relative to you, you traveled on this light clock for like an hour. On your watch, only it shows an hour has passed. But outside of that fast-moving system, other observers that don't possess the same speed are seeing their clocks going at a different rate. They don't experience the interval of time as having a different level of duration. It's not like while they look at the clock, it's starting to move like molasses. It's just a fact that the two different observers are moving through time at different rates. So the fast-moving observer that's zooming around at that high velocity is passing through time slower than their counterpart. If any of you have ever heard of or seen the movie Interstellar, there's a lot of science fiction films that kind of use these concepts in the way that they describe some of the plot. So for example, in that movie, Matthew McConaughey is this like interstellar astronaut. And so he zooms around through the universe at very high rates of speed. Then when he makes his return to the Earth, he reunites with his daughter, but his daughter is older than him, and he's comforting her on her deathbed. How is it possible that you have a child who has become an older human being than you? He's like 40 and she's like 70 years old. The reason that is happening at the tail end of the movie is because he's going at such a fast velocity through space while she remains at rest on the planet Earth. So because of the duration and speed of his travel, when he does come back, he's not as old as her. Now, you might look at that and say, this is just in the realm of science fiction and fantasy. This is not real. But this is based on real physical science. And it's not even just speculative. It's actually been well confirmed. So I have some more questions on this same theme before I move on to the next author on this topic. I'm sorry for the spoiler. I don't know if that's the only thing you need to know about the movie and the tail end of it, but it's one important scene. Okay, question. If this is true, and if time dilation is a real measurable phenomenon, then why do you think we don't notice people that, let's say, fly a lot in jets or just constantly running, or they're like speedy drivers? How come we don't see those people aging way slower than people that are relatively sedentary and that just are homebodies? If I'm running a fast, sprint, and you're just sitting on the couch, how come, my 5-year interval of time is like not like your 10-year interval of time? How come we don't have to keep synchronizing our watches because some people's watches start running slower than others relative to them? Why do you think that this effect is never noticed in human life if it is true and proven by the science? Why do you think that is the case? Because sometimes we don't move at the same pace. Some people are in planes, trains, automobiles, while others are at rest. So how come the ones that are moving fast are not seen as aging slower if this theory is true? What do you think is the reason for that? If time dilation does happen, then how come we never notice the effects of it in life? Why do you think? Okay, you're saying this. I don't really get this, but I'm going to say that they're not actually accelerating fast enough for the effect to be observable. But you do get it. You really should have a little more confidence the way you reply to some of these questions. It's because, yes, we are not able to achieve variable speeds of such a great divergent amount that these effects would be anything more than infinitesimal. So yes, it's actually true that if you are like, running really fast and someone else is standing still, you are moving through time ever so much slower than that other person is. But for these effects to be something more than on the absolute nano scale, we would have to achieve variable speeds that are much more divergent than that. And even the fastest speeds that we are capable of achieving as human beings are nowhere near the kind of speeds where this effect would start to really appear on a macroscopic level. We can maybe go in jets or space shuttles several times the speed of sound, and that's pretty fast, but it's very, very slow compared to the speed of light, which is 186,000 miles per second. And I think the speed of sound is something like, 3,000 or 4,000 miles per hour. So it's a completely different order of magnitude. But okay, if we could achieve those variable speeds, if there were a mechanism of transport for you to get into it and start going like at some percentage of the speed of light, then we would have all kinds of problems synchronizing our watches. People's clocks would run at different rates than other people's. Some people would be aging slower than others. We would have no common frame of reference that we could all organize our behavior according to. So, for better or worse, we're bounded on the surface of the Earth, and physical and technological limitations prevent us from achieving the type of speeds where these effects are easier to observe. But what we can do, and what we have done, is accelerate tiny little elementary particles close to the speed of light. So there are these big, wonderful particle accelerators that we've built in places like Switzerland, Europe, and they can accelerate tiny little protons and stuff very close, like 90% plus the speed of light. And when we do that, we see that the half-life of the particle dilates to the exact mathematical prediction of the theory, opposed to and compared with other particles that are not placed in the chamber and accelerated like that. So this is a real proof of concept. Even in Einstein's time, they were able to prove this by putting two clocks of very, very precise measurement, like that have nanoscale time measurements to like 1,000 decimal places beyond zero. And they'll put one in a jumbo jet going around the Earth, at the speed of sound, and another one on the planet Earth resting. And the mathematical formula that predicts the amount of time divergence between the two is exactly what was seen when the two clocks were reunited. Now, those are maybe minuscule in comparison to the bigger time dilation effects that would happen if things could get very close to the speed of light. But it's not so easy to accelerate bigger objects than a tiny particle to that speed. In fact, I don't think your body could withstand the g-forces involved in getting up to those speeds at all. So it's something that is not going to probably apply to everyday behavior or of human beings. But if, for example, there was some sturdy enough system where you could enter a centrifuge and spin around really, really fast, close to the speed of light, then depending on how fast and how long you were in the centrifuge, when you exited from it, the world would be so much older than when you came in. So like 10 minutes of your time in the centrifuge could be, let's say, 5, 10, 20 years outside. And that's the real theoretical proof of the concept of at least time travel to the future, if there were the mechanism and means to affect such acceleration. Okay, so very trippy and weird stuff, but we're going to continue on this. So we've got 1 more hour, and I do want to try and cover at least this last piece. So this is the work of Ted Sider, and it's also about time. Okay, Ted Sider is an American philosopher who was born in 1967, and he's still alive, doing some good work today. In the year 2005, he wrote a book, and from that book, our text has taken some material and just retitled it Time. So, Ted Sider, Time, from 2005. His full name is Theodore Sider. It doesn't really matter, but a lot of people who know him in the field just call him Ted. So Theodore/Ted Sider, Time. All right, so what's he going for in this paper? He basically just wants to try and tell the reader about some of the basic puzzles and paradoxes that arise when you start trying to think about the nature of time in any serious depth. He says questioning the nature of time is very difficult because it's something so fundamental to us that we usually just take it for granted. Like we operate with a clock, we wear a watch, we look at our cell phone and make sure that we're on time to things. We know how much time has passed, how much time is left in a given event, even in our own lives. So we live with time, but we're so used to it and we take it for granted so much that we rarely investigate it or ask deep questions about it. It's kind of just like the air that we breathe. We just don't think about the act of inhaling and exhaling the air. But if you actually do start thinking about it, it starts to seem like, wow, kind of like a labored effort. I'm constantly drawing in these breaths. Well, if you were a fish swimming in the ocean, you'd be completely immersed in water. And even if you were intelligent enough as a fish to ask these questions, you probably might not ever think, what is water though? And what is this thing that I'm constantly floating around in? So time is kind of like that for us. We're surrounded by the idea, we live according to it, but we just don't think much about it beneath the surface. But Ted Sider says we should actually try to investigate it in more detail. Reason for that is because once we start asking deep questions about it, we start to learn that the ordinary concept we have of it breaks down. And that's very disorienting and strange. But he's next going to try and show us how the ordinary concept of time doesn't make exactly good sense. One reason that he finds it very puzzling is because we often say that time moves. So I'm going to put that information here. Okay, so a puzzling aspect of time is that people say that time moves. But here's a question. What exactly does it mean to say that time moves? How are we supposed to explain the motion of time? And people do think of time as something that moves, okay? How many phrases are there, just kind of popular colloquialisms that give a sense of time moving? Have you ever heard of a common saying like that says something about like time moving or whatever? If you had any notable examples of such sayings, I'd be happy to see somebody throw one out there. A common phrase, a little idiom that expresses time moving. People say, what about time? Okay, time flies. That's definitely one. That's a well-known. Time flies. What's flight? Flight, though. Flight is, transportation through air by some means. And so that is at least metaphorically saying, yeah, time is something that moves. It flies around. It's not the only one either. Sometimes people say time is passing. Like for a thing to pass something else is for it to move beyond it. Sometimes people say time marches on. Marching is clearly a type of physical movement. Sometimes people say time is flowing. You're right. Sometimes people say time stood still, as though it usually moves, but for a moment there it stopped. Time flows as though it's like a moving river and we're just kind of caught up in the currents of this moving structure. Sometimes people talk about how fast or slow it's moving. Oh man, time is moving so slow when they're bored or whatever. So there's all these different common sayings. They're not unique to me or you. People use them all over the place, and they have for a long time. But what are we actually saying then when we talk about time moving? This is where Ted Sider says that under analysis, it stops really making good sense. Okay, and let me try and explain that. Why? Okay, so explaining the motion of time, explaining what it means to say that time moves is difficult because the concept of movement or motion is defined with reference to time. Okay, so because the concept of motion or movement depends on time. Okay, so what's being said here is that we cannot really give a clear explanation of what it means to say time moves. The reason we cannot give any kind of deep, clear explanation of it is because to say that anything moves, even just through space, requires reference to the concept of time. And so, like for example, here's my hand, okay? And what I'm gonna do with this hand that you're looking at is move it from this side of the whiteboard panel to the other side over there. Okay, so let me demonstrate. Here goes. So my hand just did the movement, or little stick figure. He's gonna walk from right here to that marker. Boom. You can't see it. There's a marker right there. So anyway, what just happened? When I demonstrated something moving, namely my hands and arms, how did they move? They moved because they were in different places, right? Like my hand, when it moves from point A to point B, it can only do that by being in different places at what? Finish that sentence. When a thing moves, that just means that it's in different places at what? What's movement require? For something to move, it has to be in different places at different, you'll get it. When something moves through space and goes from point A to B, it is being at different places at different times. Exactly, Sherry. Different places at different times. That's how something moves. If something's in the same place all the time, that's something that's standing still. So when we talk about movement, we already refer to time. For something to move, it has to be at different places at different times. So by analysis, if we say that time moves, that would sort of be like saying that it is at different places at different times. But now we're going in a circle, defining the movement of time with reference to the concept of time. And that sort of leads us in the direction of an infinite regress. If time moves by being in different places at different times, what are these second order times that the first order time is moving within? In order for that second order time to have any type of linear order or sequence, it would appear that it has to be moving within a third order sort of time, a tertiary kind of time, and on and on and on to infinity. And therefore, we would never get a non-circular explanation of the movement of time. To give you a sense of the puzzle he's trying to characterize here, he uses a couple of diagrams. So you'll see this diagram I'm going to show you here on page 458. Okay, so we have now got 4 horizontal lines like this. 1, 2, 3, kitty. She's crazy, right? 1, 2, 3, 4. Good kitty. Okay. Underneath this set of 4 horizontal lines, I'm drawing 4 different city names, starting with Boston here. So Boston, then it's New York, then it's Philadelphia, finally Washington, D.C., okay? And I'm putting the same 4 destinations or cities underneath all of these lines in the graph. Okay, so what we're going to show right here is a graph that depicts the movement of a train which departs from Boston and ultimately arrives at its final destination in Washington, D.C. Now I'm putting up here 4 time coordinates to the left. All right? Time 1, time 2, time 3, time 4, in that order from like earliest to latest. Now, the train starts off at the first time at the station in Boston. Okay, so at the earliest initial time in its journey, it's up in Boston. Later on the same journey, it's in New York City. Then subsequently to that, it's over in Philadelphia. And then finally, at the later time beyond that, it arrives at its last final destination, Washington. Now, this graph is just kind of just demonstrating how you could understand the train moving. But look, for this train to move, it has to be at these different places at these different times. Okay, now, if I draw a different graph, let me just alter the graph slightly. Now look at this version of the graph. Boston, 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 Boston. Now, in this way of looking at the graph, did this train move? Did it move or not in this graph? Maybe you'll just be able to quickly see. But let me know, what do you think? Did this train move in this way of depicting our diagram? What do you say, yes or no? Did it move here, according to this description? You know, physically, did it move? No. This is the case of a train that just was grounded at the station the whole time. It stayed there the whole time. So it's in the same place at all the different times. That means it did not move. Okay, so for something to move, it can't just be a thing that's in one place for the rest of all time. That would be a marker that stays permanently at rest if it stays in this place for all time. If it's going to move, it's going to have to be in a different place at a different time. This is a future time from the first moment that I mentioned. Now it's in a different place, so I guess it moved from a standing to a falling over position. Okay, but remember what we're asking about in the bigger picture here. We're trying to get a sense of what does it mean to say that time moves, not what it means to say objects move in time, but what it means to say that time itself moves.
So if time moves, and movement means being in different places at different times, then once again, time moving means time is in different places at different times. But we're now going in a total circle. How can you say time is in different places at different times? It is time. So how are we referring to some other notion of time in order to give a grounding definition of the movement of the initial sort? So that might not work. It seems to lead us into these impossible infinite regress puzzles. Here's another way of trying to give an attempt to explain that time moves. So he gives attempt number 2. But spoiler alert, he's going to tell you that this also is not going to fully work either. But we'll get to the reasons why. So here's another way to try and explain time moving. Okay? Maybe what people mean is that time moves because the present moment is moving. You know, the present moment keeps moving around. It doesn't stay put. Look at the clock right now, okay? If you're looking at the clock, my clock says it's 8:18 p.m. right now. So what's the present moment? It's 8:18 p.m., April 16th of 2020. But this has not always been the present moment, right? When you woke up this morning, that's the past now. But at that time, it was present. You know, you're waking up. You're presently having that waking up moment. And at that time, this was in the future, okay? But it's not the future anymore. It's happening live. Soon, this moment that is the present will be the past, you know? You'll look back on this class, this semester, this evening, and you'll be like, that was an interesting time, but it's over with. So present moment, you might say, keeps changing. When this class started, 6 p.m. was present. Now that's gone. Now 8:19 is present, but soon 9 p.m. will be the present moment. So is this the movement of time expressed through the idea of present changing its position? It sounds like it might make sense, but yet again, the author says it leads us in the direction of paradox and contradiction. So it also does not work. Let's pay attention to this graph now. So we got these 4 horizontal lines. Okay, and we're going to draw these 4 temporal dimensions here to the left, T1 through 4. Now, underneath each of the lines, what I'm going to draw are 4 different time points in a given 24-hour day, starting with noon, then 3 p.m., and 6 p.m., and 9 p.m. This graph is also shown in the book on page 459 for anybody that wants to check on it later. So each of the 4 horizontals is going to have this same structure beneath. Okay, so here maybe is the way of accounting for the movement of time. A second attempt. The present moment is moving. So initially, like in a given day, 12 noon is present. Remember earlier today, that was the present moment for a split moment, wasn't it? 12. But time passes. Later on in the same day, subsequent to the first time, 3 p.m. is the present moment. So a little bit later afternoon. Then even later than that, 6 p.m., kind of like typical dinner hour for some people, becomes the present moment. And then finally, even later beyond that, maybe heading into tonight at the end of our class meeting, 9 p.m. is the present moment. So is this a better way of diagramming the movement of time by saying that the present moment alters its position, and this is the movement of time right there? Well, here again, Ted Sider says, no, this actually is not going to help us either, because there's a problem with this graph. And the problem is these 4 coordinates here to the left. What are those? They say T1, T2, T3, T4. This is time. These 4 coordinates are time coordinates, saying at the first time it was present at noon, at a second later time 3 was present, at a third later time 6 was present. But now we're using time once again in an effort to provide an analysis of how time itself moves. So it looks like the present moment is moving relative to this time sequence. But then the problem just reappears. How are these things listed in the order 1 through 4? What gives them that linear ordering? We would have to say, well, they're moving with reference to a third order sort of time. Just build a bigger and bigger graph, and we would never get anywhere. So it looks like any effort to explain the movement of time has led us in these hopeless puzzles and paradoxes. So Ted Sider says, I've got a better idea completely. How about let's just abandon the whole effort to say that time moves and instead embrace the space-time theory of Einstein, because Einstein's space-time theory implies that time doesn't move at all. It's just a container that contains all the events of space-time. It's integrated with space, and they just jointly hold every moment that ever exists in the whole past, present, and future. All those moments are all real. None of them is more or less real than any other. And if that's true, then time doesn't really move. It just holds everything within it like space does. People don't say that space moves. They just say space is the receptacle within which events occur. And so in this way of looking at it, if we take Einstein's space-time theory seriously, and the relativity of simultaneity shows that we have to grant reality to all events, whether you think of them as being in your relative future or past, then we can no longer have this problem of explaining that time moves. But there are considerable, intellectual obstacles to fully understanding the space-time theory. So that's his next goal here. He says, a virtue of the space-time theory of Einstein is it allows us to abandon this failed project here of explaining how time moves, which seems hopeless. In the Einstein theory, no problem. There's no movement to time, so there's no thing to be explained. But to understand the space-time theory in a little more depth, I'm going to help you with these space-time diagrams, they're called. And what these try to show is the nature of an object's existence if the space-time theory is correct. Okay, so here's the way this graph looks. We have these two axes. This is the y-axis. This is the x-axis. And then going through them, we have this axis that's we're going to call the t-axis for time. Okay? Now, if this was a perfect world, I would be showing this to you in a three-dimensional space. And what you would see is that y is the typical horizontal spatial axis, x is the vertical spatial axis, and then there would be a dimension for depth. So you've got height, width, depth, and then time, the fourth dimension in the graph. This is the two-dimensional board surface, obviously, so you just have to kind of use your mind a little bit to imagine that this is like horizontal, this is vertical, they're shown in a three-dimensional realm, and this runs through the intersection of those two axes, okay? Now, in this graph, I'm going to try and diagram the existence of a human life across time. So how that would look on this space-time diagram is, sorry, just put this over a little further to the right. You would start with the initiation of the object's existence in space-time. So this is 2020 right now. A lot of you guys probably were born in this century, not everybody. I was born a while back in the 1980s, you know. But for some of you guys that are freshman age or early college, you probably might have been born around the year 2000. So suppose there's someone that was born in 2000. And imagine this person lives a really full, long, happy, healthy life that I hope most of you guys all live, and they make it to be 100 years old. So over here is the year 2100. Okay, so I don't know if I made it the biggest. Try and make it a little more legible for you. That's not going to work. Sorry. 2, 1, 0, 0. Okay, that's this hash mark here. This is 2000 over here. Now let me show you the little characterization of the human being's existence over time in this graph. Starting with 2000, they were born. Okay, there we have a graph of this person's life, and what I've put in the interior of the streak that extends from their birth date to their death are these little stick figure caricatures of like a human form. So this is a space-time diagram, and it shows the object's extent in both spatial directions, but also along the temporal dimension, which is time. So let me ask you some common sense questions maybe about the way the graph looks here. So tell me this. Why do you think the way I drew it, that the little human figure here is shorter along the x-axis at the beginning of the streak than they are at later stages along that same direction of t. Why do you think that the human-shaped figure here occupies less extension along x at the beginning of the graph than later? What do you think that is intending to represent? Why is the human figure so small back at the 2000 mark and bigger as it proceeds to the right? What do you think that's trying to show in the graph? It's the start of when you begin growing. So why is it smaller here than later? Because yeah, you are smaller in size physically. You're spatially smaller when you're born than later on when you're a full-grown adult. So you guys are full-grown adults now, but at one point in time you're a little baby that just weighed a few pounds. So that is shown by the increasing size along the spatial dimensions here as it proceeds along that timeline. Now, I have another question. Why do you think the graph is shown where there is this streak that extends along the t-axis? So you've told me why he's bigger along the x-axis as they go, but why do you think this streak shows extension along the t-axis? What do you think that stands for in terms of this human being's existence? It's not about their physical size, but it's instead what? The length that's stretched across t. What's that trying to show about the person? Not how big they are physically in space, but instead what about them? How many years alive, how much time they occupy in time. So this graph shows the full extent of their existence across both space and time. It's extended along the time dimension to indicate that they don't just exist for a split second, but that they have a duration. They exist for some duration of time, and the longer it is, the longer it would be shown in such a graph. Now, on this space-time view of physics, of ourselves, of objects, objects are claimed to have both spatial and what are called temporal parts. Now, what are those two types of parts? Spatial parts are just your body parts, the different parts of you that make up the physical object that you are. So like hands, feet, legs, torso, head, your different body parts, okay? Those are your spatial parts. But on this theory, sorry, Maria, I see your comment now, because you grow over time, can't grow all at once. Oh, Maria, no, I was just, the question there, I don't know if your comment was in response to the vertical size. If so, yes. I mean, you start off and you're smaller and you get bigger as time passes. But the temporal part of an object now is just an object at a moment of time. So we both have spatial parts, our physical parts, but we also have these temporal parts, which are like our time parts. And a temporal part is just an object at a single moment of time. So I'll put the definition here. Temporal part. It is an object at a single moment of time. An object at a single moment of time is a temporal part. Now, you have to think about a temporal part as a single instant in an individual's life existence, or if it's an object in its existence. So it's like literally just one moment in their existence. Here, let me see if you can understand this. If people take photos and post pics all over the place, right? And I'm sure all of you guys have done that, or you know people who do. So when a photograph is taken of a person and you see a still frame image of them, how many temporal parts of that person do you think are shown in the image, in a still photo of a person? How many temporal parts do you think of the person are displayed in the photo? How many of those temporal parts are there in the picture? What do you think? There's a lot of pictures of you. Take your favorite picture of yourself. How many temporal parts of you are in it? Exactly, it's one, okay? Now you gave me the right answer. Provide me with an explanation. Why is it that it's only one temporal part of you in the picture, since your common sense is giving you the right response? but we always want to make sure we're able to explain those responses. So why is it that there's only one temporal part of you in an arbitrarily selected photo or of anybody? Why is there only one temporal part in the picture? That's correct, but why? Tell me, what do you think? It's just one because, now tell me why. Let's see. Because it's a single moment in time, exactly. It's a still photo, right? What a photo does is it captures the light that is displayed off of the surface of the object that is retained within the shutter of the camera. And so it's not a video. Now, if there's a video clip of you, right? You do like a little TikTok video or whatever, really popular right now. If there was a video of a person, how many temporal parts of the person would be shown in the video? And that's a little tricky. You won't be able to give me a number, so don't even try. But let's say it this way. In a video clip of a person, there's as many temporal parts shown as there are what in the clip? There's like a little video of a person. There are as many temporal parts of them exhibited in the video clip as there are what in that video clip. Since you said a still photo is one, that's right, because it's just one moment. A video of whatever length would have as many temporal parts exhibited or shown in it as there are what in that video. You do like a little 6-second, video for fun for the internet. You say seconds, but Maria, I have to disagree with that. Why do you think I'm telling you that seconds is not the right response? Sherry, you say measurements of time. Measurements is a bit of a vague term though, because measurement could be, hours, days, weeks. So I want the unit. Seconds was a good initial attempt, but I'm telling you not quite. It can't just be the number of seconds in the video. Why so? Why do you think I'm saying seconds is not the right answer? I could just tell you why it's not the right answer, but I figure maybe you will be able to judge why this is not quite the right one. There are as many temporal parts in the video as there are not seconds, but okay, here, let's just go over it. Is 1 second the most minimal unit of time that is possible? There are many more moments in 1 second than just one, okay? Like, how far can you subdivide time down? There's half seconds, tenths of seconds, hundreds of seconds, thousands of seconds. If you ever watch certain sports, if there's a photo finish, it might be decided by 1,000th of a second between two people that cross the finish line. And you could divide time probably even further than that. Time in its smallest measurement, let's call them moments. Exactly, just call them moments, the most least unit of time. Think about it on this analogy. In geometry, when you have a line, the most minimal unit of extension on the line is called a point. In math, a point has zero duration or extension. It's like extensionless, dimensionless. There's infinity of them that compose the line, right? Now, it's maybe not exactly like that because a moment probably has to have some non-zero extension in time, but it's the minimum unit length of an interval of time. So maybe if you thought about like a camera with a very fast shutter speed, there could still be events that are faster than the shutter speed could capture. So this has got to be like God's camera, right? Like you talked about Planck length. I'm very happy to see you said that because sometimes I have to mention that to students. The minimum unit of time is the Planck length. It's something that was discovered by Max Planck, a physicist. He discovered that there's a minimum discrete length of physical space, and that correlates and corresponds to a minimum unit length of time. Anyways, there are as many temporal parts of a person as there are moments in their existence. So how many temporal parts of you are there in a short video clip? You might think infinite, but it can't necessarily be infinite. Otherwise, we would have another paradox, because that would make it seem that there'd be no way to exhaust even the smallest unit of time. If there were infinite moments in it and each one took some minute amount of time to pass, then even a 5-minute span should be an eternity, but it's clearly not. Whatever the minimum length of time is, though, there's a temporal part for each such moment. Now, this type of diagram, the space-time diagram, the way that it depicts the object's existence across time, sometimes we use the terminology of a space-time worm. That's just the way that the image appears in the graph, because it's got this worm-like appearance where you graph from the beginning of the timeline where it exists to the end. Now, if you were able to, let's say, have one thin slice of this space-time worm, then that individual deli slice of this loaf or whatever would be like one temporal part of them, like a freeze frame in a video playthrough of their whole existence, right? That's one temporal part of the individual. Now, on this account of space-time, Einstein's theory that Ted Sider is telling us that we should embrace, objects like us have got both spatial parts, like your physical body parts, but also temporal parts. And those, again, are just your entire being at every moment that you exist. And what is claimed is that all of the temporal parts are real, equally real, and they all exist, and they're just as real as your physical body parts are. So like, here's my left and right hand. I'm just looking at them. I have no doubt that they exist. The claim of this theory is that your temporal parts, not just the present one that's watching the video right now, but the future and past ones, all the way from your birth through to your death, they all are real and they all exist at all times. So isn't that so strange? You're therefore composed of both space parts and temporal parts. Now, a little more on this temporal part concept. How many temporal parts of you are sitting in your chair right now? Question. At a moment of time, like the moment I just mentioned, how many temporal parts of you were in the chair that you're sitting in? I mean, look at yourself. You've got a body. The whole thing exists moment to moment. So how many temporal parts of you are in the chair at this moment? I mean, there's a lot of body parts, but how many temporal parts of you are in the chair right now? It's, once again, what do you think? How many temporal parts of you sitting there in the chair? We got a definite answer. I just hope maybe one of you will throw it out there at me. It's not the hardest thing to, I think, deduce from what we've just said. Temporal parts of you in the chair. What's a temporal part? An object at a moment of time. Well, you say too many, but good answer if you're thinking about the span of time. But if I just asked you about one single moment, yes, there's one at a given moment. Is the temporal part of you sitting in the chair now the same temporal part that I just previously asked you about a couple seconds ago? Or is it a different temporal part now? Same or different temporal part now versus a few minutes or seconds ago? Same or different? Temporal part of you? Question. Wait for it. Let's see. There's a temporal part of you that's writing this answer. It's not the same. No, come on, Sherry. It's not the same. Why? Because each new moment, it's a new temporal part in the sequence. So there's never the same temporal part across 2 moments of time. 2 different moments, 2 different temporal parts. So it's like, here's another one, another one, another one, another one. It keeps becoming a different part with each new moment of time that's passing and unfolding. So you've got a set of temporal parts. Here's the question, next question. Are you fully present sitting in your chair right there? You, the person, the individual. Are you completely there as you're hearing this lecture? Are you fully present in your chair or wherever you're at? I don't know, you might be on a couch or in a bed, but your body where it is right now, is it fully, well, I shouldn't say body, your being. Is it fully present? It's not. No, it's not. Again, Sherry, no. But it's okay because these are heady concepts. So what's present in your chair right now is not the complete thing that you are. Because what's present in a given moment is just what? One of the temporal parts. So what is the actual whole thing that you are? It's not one temporal part or a couple of them or a section of them. It's the entire enchilada. It's the whole space-time worm as shown on this diagram. So you're not fully present. Just a part of you is there at a given time. You say, what about at rest? Like if you're frozen in ice. Not sure what you mean by this question. I mean, if you're frozen in ice for a time period, unless you're dead. But suppose that you get frozen in ice and then get thawed out again and you live through the whole thing. I mean, there's a temporal part of you for each moment during the entire process. So temporal parts don't have any duration. They last for a split second. Take, for example, an object that exists for a split second and has no extension along this t-axis, like a particle that's annihilated as soon as it erupts into existence by another particle of antimatter. That thing has got one temporal part. But you have a whole bunch of them because you exist not just for one moment, but for like years and years, okay? So the whole being that you are is the aggregate of all the temporal parts as a collection. And therefore, you never actually experience the whole thing that you are because your consciousness can only observe one of the temporal parts at a time. For example, right now, the temporal parts of your future are not things that you're capable of reflecting on because the temporal part that's watching this lecture is a different part than the future parts, okay? So I don't know if, Maria, I'm getting anywhere close to your question, but there's nothing about being frozen that's really relevant to it. I mean, objects just exist across time, and at each point of time, there's a new temporal part. All the point I was trying to make here is that though you're sitting there and you feel like I'm completely here, your physical body and the spatial parts are all sitting in the chair. But the temporal parts, there's a whole bunch of future and past ones that are not there hearing this lecture. Okay, and then Sherry, you say, so Cider is saying, your whole being is from birth to death. That's all of you as relevant to time. Yes, it is. It's the entire constellation of temporal parts stretched through both space and time. On this theory, you're supposed to take it very seriously that you don't only exist in the present moment. The present moment is not the only moment that is real. The future moments are equally real as this is, and they already exist, and so does the past. And there's a temporal part of you located at each moment that you do exist throughout the duration of your existence. So here, I'll read a little bit about it. It says here, trying to get the temporal parts. In addition to the dinosaur and some other temporal parts are represented in the diagram. A temporal part of an object is a temporal cross-section of that object at a time. Consider a temporal part of a person in the year 2000. This object is the same spatial size as the person, but not the same temporal size. The temporal part exists only in 2000, whereas the person exists at later times as well. And the person herself is the sum total of all of her temporal parts. So you would think, according to this theory of yourself, as being an object that exists in both space and in time. And across time, at each moment you exist, there's one temporal part for each moment. So on this view of reality, question I see here. I was referring to if it was the same temporal part if you're frozen in ice, if nothing changes. But I understand now. Yeah, nothing does change. I mean, the temporal part just refers to time. It doesn't even have to do with the physical conditions the object is experiencing in space. So if it exists at that time, there's one temporal part of it. Existing doesn't mean existing in a thawed out state or a frozen state or anything. It just means it's in the universe. Okay, so if we accept the space-time theory, we get the benefit of no longer having to give the difficult explanation of how time moves. On this theory, time's not moving. It's all set out. It's all laid out. All the events of space and time are fully well contained within the space-time framework. And that means that there's no change, there's no coming into being, there's no passing out of being. There's just a whole bunch of temporal parts and moments spread throughout space-time, and they're all just there. That's a different way of thinking about space and time. It's a replacement of the idea of presentism with this idea of eternalism, that all the moments are equally real, and there's no such priority or privilege that the present moment has. To understand the space-time theory even better, the author wants us to see how space and time should be seen as more similar to each other than we normally think. The consequence of this space-time theory is that time is going to be redescribed as being much more similar to space than is often thought. And the author Cider talks about 3 big similarities between time and space, according to the space-time theory. Okay, so 3 similarities between time and space. Or I'll say it the other way around, space and time, according to the space-time theory. By the way, I just want to say this. There's a lot of really heady films, science fiction films and stuff that utilize these concepts from the theory of relativity to craft, interesting storylines and plots. It might not be a perfect example, but there's this film that I thought was pretty good. It's a weird movie, so it's not for everybody. But anyway, Donnie Darko from I think the year 2000, it did explore some science fictional themes of time travel and etc. And there's a couple of scenes where main character Donnie Darko, protruding from his chest, he sees like this trail. And it's a trail that his body will end up following as he gets up and moves through space. This same line or trail has led him to his current position wherever he's at. In metaphysics of space-time, people sometimes talk about a world line that an object traces as it goes through its entire existence through space-time. So you can think about a world line that you have got also. Imagine that we could have like a trail which followed your path of motion to your current position in space, and it continues along like a track into the next directions that you will ever walk or move. And so from birth, cradle to grave, there's this one continuous world line. And you, the human, are sort of passing through it almost like a train car on a railway track, experiencing all the different temporal parts in the big space-time worm's larger existence. Now, I don't know if that visual came through to you the way I would hope, but you can always look at some of the film. Sometimes science fiction film is an apt exploration of heady concepts and brings them down to earth in the medium of art. So I don't know. I'll put that out there for your interest if you like. But back to this. 3 similarities between space and time, according to the space-time theory of Einstein, that Sider, again, is appropriating for the purpose of avoiding paradoxes, explaining how time moves. Okay, so one similarity between time and space he mentions is in terms of reality. Okay, so here's what he means by this stated similarity. So objects that are far away in space are just as real as objects that are present to you in space. And what is said here is that the same is true of time. Okay, so objects that are far away in space are just as real as objects that are present in space. And the same is true of time. Far away, just as real as objects that are present, and the same is true of time. So to explain this, I'm going to give you some quick explanation. Now, at this point, it's actually, I think, I've always thought this is a little easier to explain in our physical class meetings, because we're all in one room, and I could be like, hey guys, see this marker that's right in front of you? It's present, right? So it's definitely real. Okay, well, we're not in the same room anymore, so you're going to have to kind of use your own example. Maybe let's go with this. See the computer that you're watching this on, or whatever device, if it's a laptop or desktop or tablet or phone, you're viewing it, right? By definition, if you're watching this. So do you agree that this computer that you're watching this on is real and that it exists? Yes, obviously. I mean, it's right in front of you. You can even touch it if you want. There it is. It's real. You're watching me on it. Okay. Well, what if this computer that you're watching me on was to be removed from where you're at? You stay there in the quarantine, and I come and I take your computer and I move it over to, let's say, Arizona. So you're back here in, Orange County or wherever you're at right now. I guess some of us are split around the country now or different cities, but you're in your current location and I've taken your computer to Arizona. You're staying behind. Is it still real? It used to be real. Is it still real when it's separated from you by some number of miles? Because now it's in Arizona and you're in California. Does it remain real, or does it poof, stop existing because I put it in a different place? What do you think? Is it still real or not? the example of computer you're looking at me on. Don't be too Cartesian or skeptical. It's just common sense here. It's real now. Would it still be real if I took it away from you? Okay, good. If I took it to Arizona, what if I took it, even further over to New York? Take you to the East Coast, you're back here on the West Coast. Is it real now when it's on the opposite coast? Yes. Okay. And I'm just going to continue on the same theme. What if I take the computer that you're looking at me on right now, and for whatever reason I take it to the lunar surface and I put it on the moon? It's up there next to the American flag that we planted. Is it still real while it's on the moon and you're back on Earth? And again, the answer is yes. So let's just understand this. As far as I take this computer away from you, or any object, I'm just using that as an example. Could have been this marker or anything else. This marker is right in front of my face. It's definitely real. But if it's farther away, it's still real. And no matter how far away it goes, it doesn't start to cease to exist. It's not like objects are only real when they're close to me, and they stop existing when they're not close to me. And it's not a matter of how distant it is. I could take this thing and send it on the Voyager space shuttle into interstellar space, and like the Voyager space shuttle that made its journey starting on the planet Earth, it's still real as far away as it possibly gets. So distance doesn't affect reality. Things that are far are real. Things that are close are real, and they're just as real as one another. That's space. Now what this says is the same is true of time. And now we're talking about not distance in space, but distance away from the present moment in time. Okay, so let's think about this moment we're having right now. This is the present moment. This is 8:50, about to be 8:54 p.m., getting close to the end of this class period, April 16, 2020, coronavirus pandemic and all that. That's the present moment, isn't it? Now, you might be thinking, okay, well, what about the presidential election that's happening later this year? That's way out in the future. This moment is real, but that moment isn't real. It's farther away. What's being claimed by this theory is that no, that is real. The future moments that are any distance away, 5 minutes from now, 10 minutes, an hour, 100 years, they're just as real as the present moment you're experiencing right now. This moment is real, but it's not the only real moment. There's also all the past moments and all the future moments. So no matter how far away in space or in time an event is, it's still something real. It's not only real when it's present to you either in time or in space. So that's another claim of this theory and another similarity that helps you to deepen your understanding of it. And when we sometimes talk about the past and future, we sometimes employ metaphors that recall to mind the idea of physical space. When you talk about your past, sometimes you say, remember back then, oh, way back there where I was like so young, back as though it's behind you. And we even say that, oh, I'm glad those times are behind me, as though we're moving in a forward direction. That's a metaphor of spatial movement. When you sometimes anticipate the future, like, I wonder what lies ahead in my future. I wonder what's going to happen out there in the future ahead of me. Talking about it as though it's a forward motion towards the future, away from the past. So no matter how far, and now we're employing the metaphor of distance, but using it in terms of time, no matter how far away anything is, in space or in time, it's all just real. It's just as real as what is here and what is now. Okay, so that's a claim of the theory that reinforces the similarities described between space and time. A second similarity is one that we've kind of just briefly mentioned a moment ago, and that's in terms of parts. So I don't have to say much about it because I think we've covered it in good detail. But the second similarity he mentions is in terms of parts. And he just means by that objects occupy space by having spatial parts, and objects occupy time by having temporal parts. Okay, so the second similarity is that both things involve parts. Objects can only occupy space by having parts that are in space. And it's not just human bodies that we're talking about, body parts. I know I use that example because your body's right there and it's an obvious example, but take this table, right? It's got spatial parts too. It's got the tabletop, the legs of the table, the different parts that compose it and make it up. So to take up space, you got to have some spatial parts. To occupy time or to exist in time, you would have to have these temporal parts. And according to the idea of space-time theory, both types of parts are equally real. So your temporal parts, the bits and pieces of you that are in the future and past, they're just as real as like your left and right hand that you're looking at right there. So a second similarity is in terms of parts. Objects take up space by having spatial parts, and they take up time by having those temporal parts that we mentioned. Okay, and then the third and last similarity is in terms of the words here and now. And then that's what we're going to end with today. Next class, when we come back, I just have a couple of summary comments about Ted Sider to go over last. And then I want to just add a few remarks from the David Lewis article that was also originally listed for today. But we're doing pretty well with our schedule, so do read the David Lewis that was scheduled for today, and then the remaining lectures for next week that were originally listed for the April 16th meeting, because everything's been shifted out by a week to account for the lost week of class. Okay, so the third similarity here is in terms of the words here and now. I will remove Kitty, but just give me a second. Come on, Kitty. Are you all right? I'm almost done, Kitty. I'll hang out with you in a minute. Sorry. She really doesn't like to be removed when she's trying to hang out with me. I'm sorry. But anyways, back to this. The third similarity between space and time. In terms of the words here and now. Here and now. Okay, so explanation. These are both relative terms. Both are relative terms. Their meaning depends on the context of the speaker. Okay, so let me just end with a couple of very quick questions on this point. And thank you guys for your patience and hanging in there. I mean, I know it's tough when you're dealing with all the problems in our society today and you've got all these obligations to study really heady material, but I'm just trying to make it fun and interesting. And, you know, these are some of the most cool and weird things in contemporary physics and philosophy. So it's a treat, you know, to talk about it. But, okay, last point. This is a third similarity between space and time, and it has to do with those words you see, here and now. They're both relative terms. The meaning they have shifts and depends on where or when the speaker is talking. So here's a question. Take the word here. Can you tell me where that place is? Where is here located at? Where is here? Where can I find here? Where do I go to get to here? Can anybody tell me? What place is here at? Where is here? What's the meaning of that word? Tell me what you think. Anybody have an idea? Where is the location of here? What do you think? How do I find here? You've heard the word, you've used the word. What's it mean? Where the speaker is, exactly. So is there one universal objective place that is called here? No, it's not at all. So if I tell you here, you know, my cat is hanging out. That's true when I say it, because where am I referring to when I say here? Well, the local surroundings of me, the speaker. If you say, well, there's no cat here, and you're not a cat owner at your house, you're also speaking the truth. Because where you talk about when you refer to here is just the location of you, the speaker. If I say I'm on the phone with someone in New York, and I say, out here, we don't really have the worst coronavirus outbreak. And he says back to me, man, that's crazy because over here we have the worst. Are we contradicting each other? No, because the location referred to by the two speakers are different places because they're speaking in different parts of space. So here just refers to the part of space around the speaker that speaks the word. Okay, what about the word now? When is the moment now? That's also just relative. So if I say, what time is it now? And I'm speaking at this moment, you'll look at your watch and you'll say, okay, it's 9:02 p.m. But that same time point doesn't stay in place. So if I talk to you tomorrow and I say, what day is it now? You're not going to say Thursday the 16th. You're going to say Friday the 17th. So the point in time referred to by now is just as relative as the point in space referred to by the word here. There's no single moment basically called now. Now is just whatever moment a speaker speaks the word now at. So in the year 1920, the suffragettes that achieved emancipation for women and allowed the women to vote in the United States, we're at the centennial of that. They would say, wow, now women can vote for the first time. And that was true because when they spoke, they were talking about the time of 1920. If we say, at this point now, women have been voting for 100 years in America, that's true in our speech because it refers our word to the current time that we're speaking at. And objects, people, temporal parts of them that are alive in 100 years from now, 2120, if they say now we have the vaccine to coronavirus and we've eliminated global warming or something, you know, take an optimistic scenario, well, they'll be speaking the truth too, but that's because the word now spoken of by those future people refers to a different time. And that sort of gives the lie to the idea that there's only one moment, the present moment, which is an idea that a lot of people hold and take seriously. In fact, there's all kinds of inspirational quotes that are just filled with that idea. Now, just embrace the now. It's all that exists. Tomorrow hasn't happened yet. The past is gone. Live in the now, live in the moment. But on the space-time theory, those statements are, at least according to the view of the theory, literally false. There's not just now. It's not the only moment. The future exists. The past exists. There's nothing special about now. Now is just a word that's relative to the context of utterance. And relative to a possible temporal part, every moment is now. So just a few things for you guys to think about, some deep and interesting material on time. We're basically through the Einstein and Ted Sider. So as I said before, I'll pick up with you guys next time by finishing off this last couple comments in Sider's piece, talk briefly about some of the stuff in David Lewis's article, and then we'll be transitioning on to the next subject, which is philosophy of mind. So try to start reading Meditation 6 and the work of Daniel Stoljar and JJC Smart also. And we'll try our best to get through as much of it as we can next week. I finished grading all the midterms, but I'm going to go to bed tonight. Tomorrow, though, I'll wake up, and once I'm composed, I'll respond to any student questions by email about your test, and I can send you photocopies of your exam, so you'll see the comments. Other than that, I'm going to distribute the prompts for the next essay sometime between today and next Thursday, and then you'll have until the, what is that? We said 2 weeks hence from next week, so that's the 7th, basically, of May to turn in your paper. Am I right? Let me make sure I'm getting your dates correct here. Yes, it will be 7th of May since I've decided to adjust the due date. All right, guys, thanks a lot. Thanks for sticking in there. It's been a long day, but I hope you guys have a great weekend and a good night. Stay safe, stay healthy. If you guys ever need anything at all, let me know. And you mentioned, Sherry, office hours and stuff. I'm kind of just doing them a little bit by appointment at this time. So if you want, we can certainly set it up, and that's true for everybody. So anybody who ever wants to have like the equivalent of a face-to-face meeting, we can set up a Skype call or some type of video chat. And if you want, we can do it that way, or email. I just want to be as helpful to people as I can. So let me know if I can be helpful, and we can arrange a time that works for us both if you want a little bit of help. Okay, thanks, guys. Have a great night, and take it easy. And miss you guys. Take care. Stay safe. Bye-bye.